All right, we are going to get started for our second day of the Open Healthware Conference. Thank you so much for coming back. So my name is Alicia Seidel. I am the Executive Director of the Open Source Hardware Association. We had a fantastic day one yesterday. All of those videos are still online, available for your viewing. I wanted to remind everybody this work is supported by the National Science Foundation financially, and so we thank them very much for making this event happen. But also, I want to thank all you for being here and for showing up, for being interested in how we complete this endeavor to apply open source hardware to health and medical devices. It's been a really amazing journey for us through phase one. We hope as a community that you are all excited about this and interested, and we know that a lot of you have done work in thinking about this and sharing all your thoughts with us and co-creating this kind of new standard that we're sussing out in this journey. So thank you so much to those of you who participated, who brought demos, who asked interesting questions. Everybody also online who is participating, watching our stream, and connecting virtually as well. And then I wanted to thank our team right here. These are the people who put this event on, who have been doing all the work over the past year with this NSF grant. So thank you. Huge, enormous thanks to our team who are doing this work. And as well, yes, absolutely. I think all but one team member is here today. I also wanted to call out two specific board members, but I will say thank you to our whole board who is on this journey with us as we, apply for NSF funding and delve into completely new realms of open hardware in this truly innovative way. Lee is actually also kind of has one foot in the team. So if you are watching on the stream, say thank you, Lee. Lee is sort of our digital assets person for this conference. And then Wendy Ju, who is here in the room as well. Just wanted to thank Wendy as our co-writer for this grant, and I think has taught me an immense amount just about navigating the NSF. So thank you, Wendy. All right. And we have our standard set of QR codes, so you all know what's coming next, right? Here's how you can follow us on social media. A load of different QR codes. If you need them, take a quick picture. I'm going to pause so people can take a picture. Excellent. All right. And then the really important one that we're hoping to get people's feedback on, our survey. So this is a survey about different aspects of what should be in the source when we're talking about open healthware. We touched on a lot of these things yesterday, like a sterilization plan or testing QMS systems or different numbers like FDA, approvals or DIN specs or different kinds of 510Ks and ISO standards. So all of that, we're really looking for your feedback on what exactly should be in this new standard and how we should phrase certain things about it, how we should frame certain things about it. So all that kind of thing is in there. It should take you about 5 to 10 minutes to complete. But you are more than welcome to tell us all kinds of things in the survey too. If you want, you can take even more time. So with that, I would like to introduce the next speaker to the stage, Mike Kang. What impact do we seek for whom? Posing new framing for our collective. Mike, we got to meet him at one of our workshops, and it's been really great getting his feedback because he is a big strategy guy and also working with the Internet of Production. So thank you. I'll bring Mike to the stage.
Thank you. So when I titled this talk, I I hadn't learned nearly as much as I have at this point. So um, this is about what impact do we seek and for whom, but it's quite a bit sharper than that in terms of how I hope this is useful to the collective here and actually moving things forward in a really concrete way. So I'll get into that in a second, but I just want to say a little bit about how I got here because as Alicia alluded to, I'm not an open source person in the same way that other folks are. I'm here in partnership with the Internet of Production Alliance, and I am a strategy guy, as Alicia said, and I'll just explain a bit about what that means. So I'm from Canada. Those are some trees near where I'm from, and I do have some background. I'm an engineer by training originally, and actually, like 20 something years ago, I worked on figuring out how to carve the right shapes into the little electrodes that they shove into for the Parkinson's treatment, the electrode treatment for that back in like 2002 or something. I did that back in a past life as an engineering physicist. But then I jumped ship from there into Engineers Without Borders, which kind of connected me with this global development project with lots of quotes around that. And I learned a lot about change and strategy there and kind of bridged the gap in my career from being an engineer to being sort of a facilitator of change and multi-stakeholder complex strategies, kind of like this. This is a multi-stakeholder strategy, lots of people working together to try to change a system. So that's what I do. I help people who are trying to give birth to new paradigms, new ways of doing things, figure out how to do that. Some examples, work with First Nations on health, future of ports and trade, future of Haiti. That one's not unfortunately going so well, but that's, it's hard to change the future, but I try my best to help people be strategic in trying. And what I'm doing now is largely supporting Andrew with the Internet of Production Alliance, Andrew Lamb, whom I met when he was the CEO of Engineers Without Borders, where I worked for about 10 years. So that's how we know each other. So where the Internet of Production Alliance is that they have an ambition that's really similar in spirit to what this whole group is looking for. It's slightly different, and I'll talk about the difference. But the ambition of the Internet of Production Alliance is to create a future of production defined by decentralized manufacturing and shared knowledge. And when I talked to Andrew Lamb, who's the founder of the Production Alliance, and also Field Ready that Alicia talked about yesterday, about what are his challenges, what are you trying to change about the system, and why is it hard, basically. He mentioned that there's a lot of solutions struggle to scale up their impact, but there's a really clear need and opportunity, which I don't need to convince you of that, about how big the need is for this kind of decentralized kind of power to the people way of producing. And that the Internet Production Alliance wants to collaborate with this community, collaborate with anyone who it makes sense to collaborate with to achieve that ambition. And he asked me to help him figure out how to do that. So the thrust of my talk today is an invitation to collaborate. So success for me today is that people are excited to come talk to me afterwards, to meet with Andrew afterwards and myself, and keep riffing on everything that I'm about to talk about. So I'm going to frame that invitation to collaborate in three parts. First, I'll zoom out and share a draft framework that I've been cooking up with the Internet of Production Alliance. That's very draft. It should be draft, bold, loud letters, because the whole point is for it to get feedback and to shape it together. But the intent of that framework is to give us sort of a visual language for us to discuss and compare the different strategies that we see ahead of us and what's different about them, what's the same, what can we learn from those differences. And then I'm going to zoom in a bit more practical way and use a tool that's inspired by that framework. I'll explain more, that I put together that I hope is useful to make some progress on figuring out this not about how to make an open healthware standard that fits all the needs. So I'm going to try to be helpful there. zoom in and then zoom out again and basically ask, so what, now what? What are the implications of all that, and what do we want to do next with the Internet of Production Alliance? So starting with that zooming out, one of the things I discovered when talking with Andrew, or that we kind of, I don't know, that he explained, that I figured out listening to him, is that there's the collision of OSHWA and the Internet of Production Alliance, of open source and distributed manufacturing, is really powerful, and it comes from two different directions. And Alicia got so excited about CERN yesterday that I wanted to. This is a Large Hadron Collider image. Or maybe it's only for the nerds here they'll get the joke, but there it is. That's a collision, high energy collision between open source and distributed manufacturing. And I thought at first like that one's a subset of the other. Like if it's open source, that's a way to do distributed, and they're all the same thing. But actually, I think they're actually more orthogonal. It's like a 2x2 or like a 2D plot. So Andrew and I kind of riffed around that and got some feedback from people around this room, including Victoria and others. And we kind of realized that there are these 4 quadrants, and they're kind of spectra. It's not really a 2x2; they're spectra. But the dominant kind of status quo proprietary system, like Philips stethoscope or whatever, is the closed and centralized production paradigm. Then you've got these open and distributed paradigm, where you've got the GLIA tourniquet field ready and their whole database of things that's open, and but the whole point was about it being distributed, so it was available in the field, is ready for the field. And then you have this paradigm that's centralized and open. There's probably a bunch of other stuff there, but generic drugs and open source MRIs were some of the things that come to mind. I think Cosmic might fit there. I think Cosmic's centralized, but it's open source, if I understand right. And then you might have a quadrant where there's closed, like proprietary stuff, or maybe semi-proprietary, but only partially open. But the point, the impact that it's trying to have is it being distributed, by it being available to people. And open may be incident, or maybe a way to achieve that. So if I just kind of like look at that and keep zooming out and ask, what does it mean for our work? One perspective is that there's a shared movement that kind of intersects across open source and distributed. That is sort of like a shift away from an industry-dominated paradigm of production where it's centralized and closed, to a more community one, which is about pushing power and control of the agency out. And there are basically 2 ways to do that: open and distributed. And the best is, or probably the most powerful is to do them together, but they both are variables that can work together. And then there's these communities that come together. So the OSHWA sort of perspective or framing is open source, and the Internet of Production one is distributed. And here they are intersecting. So I think that's part of just, if part of the goal of having a community is to be more than the sum of our parts, I think it serves us to zoom out and figure out, what are we? If we're the sum of, what do we add up to? And I think this is part of it. I think it's this movement of shifting power to community. And the implication of that is that I think open source is like a part of a movement of movements that intersect at this vision of this industry-dominated, community-inclusive sort of shift in production, that intersects with things like right to repair and privacy, like the popular rage. I don't know if that's the right thing to call it, but as a systemic fraud and corruption and stealing everyone's data. Distributed production needs of humanitarian crises, like we saw in COVID and now in Gaza and elsewhere. And then, the global development system is completely just like, fallen apart, and something is going to get reinvented, and hopefully it doesn't get called that anymore. But it is a system needing reinvention. And I think all these sort of disruptions are happening at the same time. And there's an intersection with, I think, everything that Andrew's doing with the Internet of Production Alliance and what you're doing with OSHWA, and this open and distributed communities kind of coming together. So to try to finish the point on this initial zooming out bit. So if this is kind of who we are, like we're innovators in this community production paradigm, and there's people doing open source stuff and distributed stuff, and people doing both, and there's a why behind our work, like better outcomes, more freedom and agency, especially for people who benefit the least from the current system, because they're too poor, too remote, too specific. That's to borrow some language from Oshawa. And so here we are innovating in this, green sort of watermelon rind thing on the outside of industry, and we come up with solutions, but then we run into all these barriers. And Avinash had a much better diagram than this, like a more the Sankey diagram that he showed yesterday would add more granularity here. But the basic point is there's a bunch of barriers. We could talk about how to categorize them. But all these solutions that are there get kind of culled down, and hardly anything makes it a prototyping stage. So the impact that we want to be having is way less than what we are having and what we could have, and what is needed when you kind of zoom out and look at the reasons why this shift towards community is wanted, why people want it. So I actually just want to take a pause now and invite people to take out their phones. If people on your laptops, I think there's a, hang on a second. There we go. This is what I have to do. Present. Okay, so if you pop that QR code on your phone, or if you don't have your phone, if you're on your laptop, you can go to menti.com and type in that number up there, that 8-digit number. And this is a bit of an experiment. I haven't done this in a long time. So the first question is, I'm just curious, when you think about your work or that of your organization, and you can pick up to 2, where would you place yourself on this spectrum? And just thinking about how people mention things like, we're open source, but we have a proprietary bolt on top, makes sense. You're kind of a blended model. And some might produce some things centrally, some decentralized. So I just want to see what kind of diversity we have.
May I ask you where we are or where we want to be?
That's are.
Okay.
We could probably do it twice, and that would be an interesting comparative. Yeah. Are. I'm just curious. I know we're not supposed to do questions, but just one, if you'll indulge me. So to me, I'm neither surprised nor not surprised about this. I didn't know what to expect. Is anyone surprised by what they see, or is this about what you expect? Any surprises here?
We can't see what 6 is.
Sorry?
We can't see 6.
Oh, yeah.
Well, at least there's one, it's me.
Yeah. Are there any surprises? Not really. Okay. Well, good. That means we can move on. So I guess one thing that I do take from this is that one thing I was kind of wondering is if we were all going to be clustered in one spot, but there is actually mostly a diversity here across this spectrum, which must mean something. I'll think about later what it is. But the second question is just thinking about this framework I showed, given that the intent is to sort of give us a visual language to talk about what we're doing and, write it down and compare it. That's the intent. I want to invite people to take maybe about a minute and share what would you change about this framework to make it more useful, accurate, or complete. Don't worry. Obviously, there's a lot more to think about than you can share in that amount of time. We can talk about more later. I just want to kind of get a check in. So maybe I'll give you 30 seconds actually to do that. Okay, great. That's enough to get us rolling. Just for the sake of time, I'm going to move on. So if you were in the middle of it, sorry to cut you off, but I just want to keep us moving, and just and we'll, you know, there's lots to discuss here, so it's just a starting point for the conversation. So sorry, I need to go back to my slides. Okay. Okay. So on to part two, which is to zoom in. So I want to just share a reflection that I had about this design challenge of coming up with a certification or a standard that serves our impact. And when I was in Boulder in last month, and then in the workshop in May, and just listening to people, there were a few ideas that I heard floating around, and you can read them. But the basic thing that I heard sort of in tension was that we need something that both serves transparency and discoverability of solutions, that makes it easy to find stuff, and a standard. And these things are kind of there's like sort of a dynamic tension in play. Alex Baldwin mentioned yesterday that tension with the FDA, and there's sort of a dance that you have to do. And I think this is an example. This is an example of that transition from industry to community. Is sort of like us bumping into the difficulty of it. I think is partly in figuring out why it's hard to come up with a certification, because I think there's a couple of things that are in polarity. So I just want to introduce a tool called a polarity map, and basically this is a tool that is useful for basically finding your way out of analysis paralysis when you're facing some kind of design challenge or relationship challenge that can be polarizing, confusing, fearful, shameful, and you have to make choices despite the difficulties. And a polarity is basically a dynamic tension between virtues. And a really clear example, or that I find clarifying, is breathing. There's no correct middle ground between inhaling and exhaling. You're not looking for the balance in that tension. It's a dynamic balance that's always in motion. So using polarity language, the poles are inhaling and exhaling. If you only do one or the other, so do one pole to the exclusion of the other, you die. If you frantically oscillate between the poles, that's not healthy either. You're hyperventilating. And a dynamic balance between them is healthy breathing. Okay, so some of the images aren't working. I'll just go to the one that works. So the way that you map a polarity is you start by saying, what do you want and what don't you want? So what do we want? Life. What don't we want? Death. Inhale and exhale the poles. Why do we inhale? What are the benefits? To get oxygen. Why do we exhale? To get rid of CO2 and to make room for more oxygen. If we inhale and never exhale again, so inhale to the exclusion of exhaling, I think we first pass out of hypercapnia, then you die of hypoxia. But just for the sake of the framework, just say you die of CO2 toxicity, and then exhale. If you only exhale and never inhale, you'll die of O2 deprivation. So that's what a polarity map looks like. And polarities are everywhere, or at least I see them everywhere. These are some examples that you'll probably recognize. And so the question then is, if there's a polarity in play here, this dynamic tension between virtues, what is it in terms of designing this open healthware standard? And if you're with me still, I think the things in tension here are sort of formal certification and a community signal. So a formal certification is standards-based, centrally governed, verifies whether something meets a formal definition. Community signal is more lightweight, bottom-up. It's more about usefulness, provenance, popularity. And these things they're not incompatible, but they are in polarity. It's hard to see exactly how to do them both well. That's what I think anyway. I guess we'll find out when you give me feedback. But so what we want is adoption of open source and distributed healthware solutions that improve outcomes in agency for underserved populations. We don't want solutions to not be found, saturation of junk, untrustworthy quality, non-adoption. So one of the benefits of like the formal certification, so if everything goes well, like that pole of formality at its best, you have a standard that promises everything will be buildable without a paywall, consistency, proof of prior art, which is important for various things in IP. The benefits and values of a community signal. So a community signal at its best is low barriers to participation. It is connected to other movements that are not necessarily like certified open source. So one of the examples that comes to mind is like OSMS that Victoria will be presenting on later on. Like it is an open source thing, but she also like the bar of what you have to clear to be considered open source in that database is super low. It's much lower than what a certification would be. So like the benefit at its best is inclusion, basically. Like everyone gets to participate in the signal if at its best. But if you focus on certification to exclusion of community, like a formality to the exclusion of community, you risk creating a standard that only open source evangelists care about. I think that is a risk that, that we just sort of want to convince the world that open source is a good idea, and that's sort of like a gateway that you have to pass through in order to work with us. I think that's a pitfall of that pole. And then the other pole, if you focus on signaling to the exclusion of formality in a certification, you get lack of consistency, like junk saturation, hard to distinguish between signal and noise, like what's actual good design versus abandoned prototypes versus marketing fluff. Like an example is if you have a very simple standard where you just have one checkbox that says medical, that's nice and simple, low barrier, but maybe everyone and their dog clicks the checkbox and you have like 10,000 things that all say they're medical. So would be the degenerative side of that pole, of the community signal pole. What happens if you focus on signal to the exclusion of certification? So the way that you use a polarity like this is you basically ask two questions. First, you map it out and you write down the four poles and you say, or the four quadrants, and you look for the benefits and the fears on both sides. And then you essentially ask two questions collaboratively. And if we had a longer workshop, we could maybe have these discussions. Basically, what can you do to maximize the benefits of the good stuff? Like, what actions and strategies can you employ? And what warning signs do you look for that you're focusing too much on one side without paying enough attention to the other? So I don't have any answers here, but the offer, the hope was that if by kind of exploring this tool and looking at these four questions, what are the actions we can take to maximize the benefits, and what do we look for to avoid the pitfalls? Maybe collect some sort of collaborative design input there. And then see what comes up and see what wisdom we have in the room about what that means for what a good standard looks like. So if you'll indulge me again with Mentimeter, just one last time, there, yeah, if you pull up the QR code, sorry. And yeah, so there are 4 questions. I'm actually realizing we're not going to have time to do this. So hang on, let me just do some real time adjusting of my plans here. Don't worry about doing the Mentimeter. We can talk about how to explore that later on. I just want to make one last point and then make the invitation for next steps. So sorry, I just need to scroll through here. Okay, so in this framework here, we can think about whether there's maybe a survey or something that we can use to talk about this, or maybe I can talk with the Oshawa people about whether there's actually something here. I'll get your feedback about whether this polarity even is useful to consider. But just to get to the so what, now what of where the Internet of Production is and all of this thinking. So just noticing that, like, that polarity, that sort of formal certification and community signal, it sort of mirrors the other one we talked about the shift from industry to community. Like there's sort of a microcosm. So like I mentioned before, I think like what we're figuring out by figuring out a good open healthware standard is part of that bigger sort of transition. And there's actually you can use this polarity map to think about what we want in terms of systemic change. So if we want to shift from a paradigm of industry to community, the current state is that it's out of balance. Like we emphasize industry to the exclusion of community, and we end up with things like exclusion of small market minority needs and human sacrifices at the altar of the market, high barriers, monopolies, low innovation. All that stuff happens when you kind of suck all of the power of production from community and put it in industry. And Anthony's going to share a perspective on the history of how we got to this situation of where industry sort of is out of balance so much. And this, like the future vision that I think that intersectional movement of distributed and open source wants is a balance, a desired future state where industry and community are sort of healthily breathing, and we're getting both the responsiveness and the power economies of scope that comes with the community production power and the economies of scale that comes with industry. And then what people are going to fear and people are going to accuse you of wanting, and Andrew tells me that this comes up, is like, oh, you just want to tear everything down and do everything locally, and you don't pay attention to any of the benefits. So this is the nature of polarization. You only talk about the benefits on your own side and the downfalls on the other. So this is one of the ways that the status quo kind of defends itself, is by stoking fears. And another way is by pointing out that, well, our system, whatever, cured polio or in this country or that country, and without being able to see like why it's what the flaws are. So this is a way you can kind of use this polarity tool to think about strategy. And I think if this is the current state, this is what we want. There's basically 3 moves that I think we're making. I think Oshawa does a great job with 1 and 2. Alicia, you keep mentioning marketing. Yeah, educate people about the benefits, address the fears. There's a gap as well in terms of accelerate. Andrew and I and the Internet Production Alliance want to build an accelerator that helps people basically break through all those barriers and like increases throughput of innovation, of like actual solutions going out of the prototype stage and getting into people's hands. And basically that the invitation is to work with Andrew and I to figure out what that means and how to do it. And that's it. Thank you.
Thanks, Mike. So next on the virtual stage is Andrew Lamb, who Mike also just mentioned and works with. Andrew works with the Internet of Production Alliance, which is pioneering open infrastructures for distributed manufacturing. He's also working on the local procurement learning partnership that emerged out of his work in the humanitarian relief sector as a way to help aid agencies buy locally made supplies. Today, Andrew will be sharing his virtual talk, Humanitarian Making, How He Showed What Was Ready.
Good morning, New York City. Always wanted to say that. My name is Andrew Lamb, and I am the chair of the Internet of Production Alliance. I'm sorry I can't be there in person in New York today, but greetings from Sydney, here in Australia. And thank you to OSHWA for putting this event and indeed the Open Healthware project together. It means a lot to me, and I think it'll mean a lot to the world as well. I hope the conference is going well. I know you've just heard from Mike, who I'm collaborating with at the Internet of Production on some ideas for a sort of wider program of activity around open source healthcare medical devices and their production around the world in places that often, particularly for places that often lack access to them. So Mike has been talking a little bit about, has been framing the conversation, his contribution, I think, a little bit about the sort of the spectrum between stamp and signal, or the way I'm thinking of it is between sort of certification and community, or community and industry. There is a gap there, and I'm here to talk to you a little bit about what we did in the humanitarian sector to try and fill that gap between community and certification. The talk I'm going to be giving, the tools I'm presenting, draws heavily on my time working with Field Ready, and I particularly want to acknowledge the work of Bryn Mawr John, my colleague from Wales in the UK, who developed a lot of the tools that I'll be showing you today. The other thing I'd like to say is that OSHWA is quite an important part of the process, and you'll see that. So the OSHWA certification became quite important to us as a way of sort of demonstrating to the wider humanitarian sector some form of certification. Now, it may not have been an ISO standard, perhaps, and it was a certification as open hardware, but it provided a kind of understanding that someone else had checked these designs. Right. Let me show you the first picture. In 2015, Nepal suffered a pretty serious earthquake, and all sorts of different parts of the country were affected, mainly in the mountain areas, and Field Ready was just getting started as a humanitarian organization. And I went out with my university friend, my colleague, Mark Mellers, who you can see in the center of the picture here, to try and figure out how Field Ready could begin to transform the traditional aid supply chains by making supplies in the field. So here we are, we hired a vehicle, we drove to a displaced people's camp, people who'd lost their homes in the earthquake, and we started 3D printing some supplies that they needed. And for the last 10 years, this happened about 10 years ago, for the last 10 years, I have been involved in improving this process, trying to share this process, building on local manufacturing capabilities as much as possible, trying to improve the quality of what gets made, the capabilities where things can be made. But it became pretty clear to me early on that a killer app for distributed manufacturing, which is now the focus of my work at the Internet of Production, was medical items, health and care items, because they were small volume, high impact, and often quite unusual devices that they didn't, they weren't mass market products, and they didn't always get to where they were needed. Certainly the clinics in Bahabise really struggled to get some of the supplies, even from the Ministry of Health in the capital city. So one of the things we did is we started an apprenticeship program. We developed a series of health care, medical, 3D printable products that could be implemented into the field. So this is my colleague Ram Chandra Thapa, who I'm still working with even today. And he was our first apprentice. He would visit some of the rural clinics, find broken things and fix them, or find supplies that are needed and make them with a 3D printer right there. So this is a part for an oxygen splitter. And the thing about this is that this is actually not high-tech, high-end medical devices. These are really simple items, often single 3D prints. Over time, we realized that there needed to be, as the things we were making got more advanced, and we made more and more of them, had more and more designs, there needed to be a way of organizing them. And we also faced difficulties selling to aid agencies, because locally made things, and things we were making ourselves, often just weren't certified. And procurement policies somewhere would say that an item had to be certified for, say, the Red Cross or Oxfam or UNICEF to purchase it. And so we got a little bit stuck with our business model here, because we were like, well, we can enable all of these local entrepreneurs to make these things, but then they can't make any money because they're dependent on aid grants rather than business procurement opportunities. So certification reared its head there in conversations about procurement. There's also the question in distributed manufacturing for how you do quality control. And so we ended up with a sort of internal review system and self-certification systems where we'd use standards for particular products, but self-certify against those standards. And we do that ourselves internally to try and overcome some of these problems. We were in this gap between community and more formal internationally recognized certifications. So what we did, let me just share again. What we did was came up with a product development process that included a rating system. So by RAM, and let me show you this. This is our catalog of designs. And what we came up with is a series of rating systems. So we called these field readiness, which was about, how ready is it to go into the field? Maker readiness, to what level is the documentation in a place where someone can easily reproduce the item? User readiness, like do we have good documentation about the the use of the item. Technology readiness, is it a prototype? Is it an emerging project? Is it something that's actually being used, tried and tested? It's roughly equivalent to the technology readiness levels. And risk readiness, you know, to what extent have we analyzed all the risks, done the risk assessments, mitigated those risks? So, and this was again sort of an internal system, but one that we started using externally as well to share with others how our open hardware designs could may or may not be ready for them to use, how ready they were to use. So some of the medical implements, if I just filter this by health, I'll filter it by Nepal. I'll show you what we did in Nepal. We did a number of medical implements. So here, basic tweezers and forceps, a wrist brace that could then be molded, aimed at children who might have fallen, broken their wrist, a fetoscope, and finger braces. We did a range of different things, and often these are single 3D prints that you can download and make. And what you're looking at here is an Airtable database that is still up and running, that contains all of these files. And you can click on one of these. So if I click on the tweezers, you have the readiness levels and some of the production cost and estimates. We've got some pictures, we've got production drawings, and we had all of these things in here to do with the, you know, showing really how complete the documentation is. I'm sorry, I'm a little bit distracted. There's a parrot trying to, he wants me to feed him. Right. Yeah, Sydney has parrots, so there's one at the window waiting for me to feed him. Right, so we had this portfolio, and the risk readiness ratings emerged over time out of this. Let me share this document with you. This is a brief description of the different readiness levels. So the 5 levels I've read to you, and then a little bit more information about what the different ratings mean. So, for example, you know, if the field readiness is very high, it's because, you know, we've had good community feedback. It's easy, it's robust, it's replicable, easy to use, things like that. Here's the maker readiness measured. It's a little bit like how easy or hard is something to make, and you know, a single 3D print might be pretty easy, but you know, the sort of chillers for MRI scanners that my colleagues were making in Syria, that might be a little bit more expert. User ready is, you know, is it very well, the highest level, is it highly suited to user needs, desirable, ready to be used as intended? You know, it's not really something that people have to have workarounds to get to use. The technology readiness levels simplified down to 5 levels here. And then the degree of risk here. So, and this could be risk throughout the process, but particularly to the end user. And we had some, you know, reasonably high risk devices such as heavy lift airbags. So we had processes to test those, and that was the rating system, and we applied it to the different designs as part of the product development process. Now, there's a couple of other things I want to show you. We had let me show you the product development process, in fact. Since this is a show and tell, so let me share this one with you. Again, recognizing my colleague Bryn Morjon for putting this together, trying to articulate how we did things. Sorry about the parrots. Right, if you can hear that. The process was always started with the need. We'd go through a triage process about trying to understand what the most effective use was. We'd come up with some specifications, we'd start the documentation, then hopefully they start looking to see if something already existed before coming up with some designs. Engineers really do like to jump into designing things as opposed to looking to see if there's already open hardware solutions out there that they could use. And then we had an iterative human design process. You'll be glad to see in our product development process, we also tied into the open know-how system, the standard that the Internet of Production developed, which I will share with you, and the OSHA certification as well. Now it says here, Aziz to add description. My colleague Aziz at Field Ready did lots of different roles, but one of the things he did was get all of our designs published under the OSHA certification and to get them all open know-how manifests. So big shout out to Aziz for the work he did on this. In fact, he was so busy he didn't manage to quite finish that diagram. But yeah, a lot of what I'm showing you here is made possible by him. So let me tell you what the open know-how standard is. Now that I've shown you a little bit about the readiness levels and the product development process at Field Ready, if I go to the browser again, the open know-how standard was intended to solve the problem of how do you find 3D models of tweezers on the internet that you can download and use. This is the challenge for a lot of makers, is knowing, is this model any good to use? So if you type in tweezers 3D model to a search engine, yes, you might get model giraffes being pushed at you, but it really is really unsure, like how do you know which ones to find? Now, if you happen to know, if you're fortunate enough to know anything about 3D printing, at least, as opposed to all the other manufacturing processes, you could go to something like Printables, type in tweezers, and then you get lots and lots and lots of tweezer designs. Again, how do you know which one to use? And some of them might be, say, on Field Ready's repository rather than in Printables or Thingiverse or wherever it might be, Wikifactory. So we came up with the open know-how standard, and this was an attempt to help the discoverability of open hardware and proprietary hardware designs. And this is a little bit about the project on the Internet of Production website. And if you click on View Specification, you'll see in here the beginnings. This is the beginning of the document, but let me show you further down. You get a little bit more into the specification itself, including some references to the the readiness levels, the risk ratings, and things like that. So we sort of built in some of what Field Ready had learned through its rating systems, but also all of the other contributors to the open know-how standard, in order to, like, here's the stage of development, basically, in order to try and help use this data standard for when people are searching for things on the internet, they can say, I want a finished product. And we've got this online tool where you can fill in the manifest. There's only a few required fields, but obviously the more the merrier. And you can go onto here, and somewhere there's something like development stage, and you can say it's a prototype. And then once your manifest is ready, you can download it, put it on a web-facing server, and you have an ability to try and to make your designs more discoverable. There's about 1 million items that now have open know-how manifests. But one of the things we get, the requests we get, is like, can there be a tick box for health and medical items, or humanitarian items, or whatever it may be. The parrots have gone now. Okay, we haven't done that with open know-how. We might do it in future versions, but it would be interesting to see what comes out of the Oshawa's Open Healthware project, to see if there's something we can do together. The last thing I want to show you is the humanitarian making website. So we summarized some of Field Ready's work and work of other organizations, and have published the readiness levels on humanitarianmaking.org, which is a fairly basic website still at the moment. And but a lot of the documentation, the internal documentation I showed you, is now available publicly on this website as well. And humanitarian making is not it's not health specific. It's about trying, I started it to try and bring aid agencies together and to make distributed manufacturing, local manufacturing more normal in the humanitarian sector. But the learning we had from Field Ready, because a lot of what we did at Field Ready was pioneering this stuff, is shared with the humanitarian making community and on the website. I think that's about everything I wanted to show you today. Sorry about the interruption from the parrots, and I'm sorry I can't be there in person. Enrico Bassi is a long-time collaborator of mine. I think he's speaking later today. So he knows a little bit about the Internet of Production, the kind of work we're doing. And Mike Kang is working with me on the idea of a broader program around the distributed manufacture of open hardware, health, medical supplies. So you can have a chat with them, and you can get in touch with me through LinkedIn, things like that. So good luck with the rest of the conference. Take care, New York.
I love Field Ready. So next speaker is Dara Obademi. Dara is an electrical engineer actively working at the intersection of open source hardware and the Internet of Things. He was named an Ada Lovelace Fellow at the 2022 Open Hardware Summit in recognition of his contributions to the open hardware community. Dara is a passionate advocate for leveraging technology as a powerful tool to address some of Africa's most pressing challenges, with a particular focus on accessibility, innovation, and impact-driven design. I'm very excited to have words, even if they're virtual, from our international community, so very thankful. Please welcome him in his virtual talk titled Open Healthware: Expanding Access to Medical Devices in Africa.
Good morning. I greet you and I welcome you to this year's Open Healthware Conference. My name is Oluwadara Opademi. I'm an hardware engineer, an electrical engineer, and an advocate for Open Healthware from Lagos, Nigeria. Today I'll be speaking on the topic Open Healthware: Expanding Access to Medical Devices in Nigeria. Over the course of this year, I've joined sessions by the Open Source Hardware Association, for the open Healthware researches and discussion. And also in 2022, I was one of the other fellows selected for the Open Hardware Summit. Work with me and see how we can expand access to medical devices in Africa. So I like to put proper context into things. I like to start with a definition. What is a medical device? So I got this definition. A medical device is any instrument, apparatus, machine, appliance, implant, reagent for in vitro use. It could be software, it could be material, or any related article used for any a specific medical purpose. So let's look at the state of medical devices in Africa. Today, as it stands, 2025 in Africa, the market revenue for medical devices are around 9.64 billion, with an annual growth rate of around 6.65%. So by 2030, the market value is expected to hit 13.3 billion. Let's look at indices. How accessible is medical devices in Africa? Today, we have over 40% of healthcare lack basic equipment such as blood pressure, you have thermometers and the likes. And what are the key segments? We have the cardiology, orthopedics, ophthalmology, cardiology relating to the heart, orthopedics for motion, movement, the limbs, ophthalmology, the eyes, diabetes healthcare. Also, you have some notable companies that play in the medical devices space. You have Retiva Healthcare, you have Zipline. Zipline is a tech company that uses drone for drug delivery. Then you have a lot of foreign companies also playing in the market. You have Philips, the Healthcare, and BD Africa. So let's look at the progress. What has the progress that has been what are the progresses attained in medical device development in Africa over the past years? You have regulatory frameworks. You have a lot of countries now coming up with regulatory frameworks. Countries such as South Africa, Ghana, Kenya, Egypt, all now have active medical device regulatory agency. And local innovations, there are local hubs springing up within the region, doing things around 3D printing. And so you could now 3D print prosthetics. You have manufacturing. There are small scale device production companies that produces medical devices, tools around the continent in Nigeria and Kenya. And you also have digital integrations. You have companies that are now integrating a lot of solutions. So mobile diagnostics, solar powered devices, Africa's huge problem of energy. So a lot of companies these days are introducing solar powered devices and also remote monitoring solutions. And also there are also regional organizational efforts within the regions. There are training programs, there are partnership with global organizations such as WHO to advance this to support all of this advancement within the region. So what are the challenges in medical device adoption? So you have regulatory weakness. So because you have to move from country to country, so it creates a lot of gaps. So different countries with different regulations. We need to. It's a challenge that needs to be overcome. We need to create an harmonized system of regulations within the region so that this can also help in deployment of medical devices. You have local manufacturing. The African market today is still heavily dependent on import. There are low R&D investment, low R&D, and this low R&D investment creates supply chain gaps. We have weak infrastructures. There's still a lot of infrastructure deficit within the region. And this all contributes to medical device adoption and technical capacity. You have a lot of technical gaps. So we have trainings and people coming up now, but you do not have to the required number of people to that have you don't have the required number of people who have this required skills, and also um, ed, um, technical assessment. You have also within the region also, and these are ways we can use, we can see to look at how open Healthware could fill this gap. So what's even this open Healthware and open source hardware movement that I've been talking about since the beginning of this speech, and why we are also gathered to make discussion. So according to OSHWA is the Open Source Hardware Association, and it defines open source hardware as uh, physical items whose source file, the codes, the designs, they are openly shared. And this allow anyone to really copy, modify, distribute, and sell or design. And also, what OSHWA seeks to do is to empower individuals to control their technology while fostering knowledge, sharing, and commerce to open design exchange. And and but now, out of this movement, we carved something called Healthware, and it's now a specific application to all of these OSHWA principles to the healthcare sector. And it's a movement that has been, and it keeps evolving. So what has been the impact of open source hardware in Africa? The open source hardware movement is really having a significant impact in Africa, particularly when you look at giving access to healthcare, education, innovation. So today, very active on the continent, you have the open source, the software part, and people doing things around the software. But the hardware part also is also coming up. And what are the things that the hardware um, um, movement has helped to achieve? So it has helped to achieve increased access when you for materials either in healthcare, in education. You now have open source designs for ventilators, open source designs for microscope. These are enabling local fabrications and addressing the shortages. Rapid crisis response. You have faster production of PPEs and diagnostics tools, especially during emergency. And that played a part during the COVID-19 emergency. You could see different ops just getting designs and printing out things that are needed. Also, cost reduction. So there's a lot of reduced price. So compared to what you get in the market. So an open hardware can be 5 to 10 times cheaper than commercial alternatives. And why is this possible? Because some of the materials used in production of these devices, of this instrument, are locally sourced. No imports, and also all those costs are totally are removed. And sustainability. So with open hardware, you can now recycle materials. You can have materials that are repairable, and all of these are guided by open sourceware, open source hardware principles. So to also put a context within the continent, there's been the Africa Open Sourceware Hardware Movement, holding conference and creating programs. In my country here in Nigeria, we have the V Square Makers, of which I'm part of. So it also promotes the principle of open source hardware, hosting hackathons for students with different regions and solving problems from healthcare to education. So in this part of my talk, I will just talk. I would highlight some innovations that I've seen got to research on while preparing these talks and the impact they are creating within the uh, healthcare healthcare sector, especially in producing medical devices. So I will start with Respira Works. Respira Works started in Berkeley, and also you now have about 200 people who have contributed so far, and some of these people are from very rural communities. They are from developing countries like India. Productions are also going on in countries like India. My friend who told me about this uh, initiative was part of the people who contributed to it. So what Respira Work does is providing not low cost open source respirators for underserved communities globally. And what were they able to do? They were able to open source software and hardware for global access. Anywhere, anybody in the world could access it. And now they've been able to create respirators that are affordable under $2,000. So that's reducing the price of the average respirator by almost uh, 5 times, not even more than that. And so it has also helped to optimize supply, the supply and availability of these materials to to local communities. And you have full featured design. So they've been able to also design to be able to to use cases, use scenarios of these local communities and to adapt also with their challenges, either challenge of um, power and the likes, and also while still doing its main core function and supporting advanced technology and regulatory ready. So they've been vetted, safe to use across regions. And you could see a lot of people are still contributing also to improve this technology. This is uh, an example of how open source hardware design can help to advance medical care, and it's all encompassed in what we call the open healthware. So also one I found a very interesting uh, uh, initiative or design. It was called the Leverage Freedom Chair. And Leverage Freedom was a low cost, lever powered altering wheelchair. And this was initiated, the idea came while Professor Amos Winter, then a graduate student of MIT, was taking a course on wheelchair design. And he had this fellowship to come to East Africa to experience, to see for himself what people were going through. And he saw that the normal wheelchair could not go through some of the rough terrains, were uncomfortable, could not be detachable. And this came back to like, he went back to his lab and started working on this low cost leverage freedom chair. Another thing was to incorporate the design of a mountain bike. So the rough and high terrains, people could use it. And what you had, the result was a lever powered wheelchair, which is about mechanically efficient and could provide 80 to 50% travel time, even on tarmac, had more torque. It was adaptable, it could be used indoors, it was removable, and also it could be maintainable. It was maintainable, so you could get parts from every local bicycle repairer. So that meant every bicycle technicians would help fix and maintain this chair. And by the time he was able to do this, it cost the price of producing was very low. And that's one of the things open source hardware brings to the table, because locally sourced materials were used for it. You now have the price around $200, equivalent to what you'd have for maybe about $1,000 or $2,000. And this is a very good initiative. Though it runs as a non-profit, but it's just an example of how we could create access to medical devices, especially for people who need them and people who are in that situations. They understand the situation better. We've given them the technical power for production, and now they could produce all of those devices. So I'll end with this um, initiative that was sponsored by the uh, UNDP, and it was 3D printing for prosthetics, and they helped to launch 3D computer designs and manufacturing prosthetics in 2022. And what did this do? This new technology, it reduced the production time from 2 days to an hour, uh, enhanced quality. It replaced the time consuming, the manual process involved in producing quality limbs. And what it also did was it increased the access of people with disability to some of these devices. So globally, we have less than 20% of about 30 million who are in need of access to some of these limbs. And what did they do? One thing I really found interesting while doing my research was that local technicians could now build this thing. They could print this thing for people in their communities. And that is one of the impact that open source hardware could provide. So can we as a movement open source even designs of 3D printed machines that local materials can be used to produce? If 3D design machines are produced locally, then you could have more of these prosthetics um, uh, printed even within local communities, creating access for everyone. I have limited time. I'd like to end my talk here. You could reach out to me via my email, daraobademi23@gmail.com, or you could reach out to me also on LinkedIn, Daraobademi. And I implore everyone in the all to join the open source hardware movement. I'd like to say that it's time to really see beyond the conventional, closed IPs. You could take a trip during your summer break to Africa, see the problem for yourself, get some of those research funds in your lab, and produce some of these devices, or even at your spare time, and open source them. You don't know who could see those designs and take them to the next level for the local communities. You're not just creating devices, you are saving lives. You are empowering people and giving power to everybody, from the medical doctor to the artist to the technician on the street. What open source Healthware does for us is gives us power to make things. And we are all makers, we are hackers, we are all based, and this is what I know we enjoy doing. So let's keep doing, sharing those designs, sharing those source code, and solving problem for everyone in the world. Thank you once again for having me. You have a wonderful conference. Thank you.
We're gonna take a break. Be back at 10:40 for lunch. If y'all have any devices that you want to show, it was really fun yesterday. So if you just happen to have it or you want to go grab it real quick during the break, you're more than welcome to share your devices again during lunchtime, just in the same place. I also just want to add that, yeah, I'm really, really thankful that you all are here. Feel free to get some coffee, some tea, whatever out there. But yeah, just be back at 10:40. Thank you. Hi all, we're about to get started. If you want to find a seat. Cool. All right, y'all. The next speaker is Victoria Jacqua. Victoria is a founding member of Open Source Medical Supplies. She is also the OSMS Medical Community Lead and Curator for the OSMS Project Library. She is a steering committee member for the Global Open Source Quality Assurance System, the product owner for their flagship product, Global Distributed Tracking, serves on the board of Public Invention, and is the project lead for the Open Source GLIA Tourniquet. Joining us virtually to share her talk, The Legacy and Impact of Open Source Medical Supplies, OSMS, 2020 and Beyond. Please give her virtual talk a warm welcome.
Hello, everyone. Thank you for attending the Oshawa Healthware Conference. My name is Victoria Jacqua. I am the Medical Community Lead for Open Source Medical Supplies, OSMS, and I'm very blessed to give a virtual presentation today. A little bit of technical housekeeping. I will be doing a slide share, but in between, I will be showing some videos and also walking you through the OSMS website briefly. So I'm going to start with that slide share. So the legacy and impact of OSMS 2020 and beyond. Contrary to popular belief, OSMS does not manufacture any product. We do not own any designs. There are no OSMS open source designs branded. We exist to curate, document, organize, collaborate, support, and elevate the efforts of the open source medical hardware community, whether it's featuring your open source medical design in our project library, celebrating your efforts in our newsletter, creating collaborations between organizations who may be working on a project, or otherwise supporting the ecosystem of open source medical hardware. In March of 2020, our then co-executive director, Guy Cavalcanti, switched a Facebook group focus from open source ventilator to open source PPE because the demands of the healthcare situation at the time demanded PPE. And we have to remember that in March of 2020, there were no open source PPE designs. That was not a thing. And in fact, open source medical hardware as a concept, much less a scaled idea, was in its absolute infancy. There were some niche projects through universities working on open source medical hardware, and there was one organization in Canada called GLIA, who was founded in 2014 and published the very famous open source stethoscope in 2018, that was really pushing forward the idea of open source medical hardware not only being R&D'd, but manufactured at scale in an affordable way. But in March of 2020, that's all there was, and there were no open source PPE designs that existed. So until June of 2020, when the OSMS website debuted, OSMS, the organization, was run exclusively by volunteers. We ran a 70,000 person internationally represented Facebook group page and produced a set of Google documents called the OSMS Medical Supply Guide, which is still current today. The OSMS Medical Supply Guide not only informed the public about how COVID-19 was spread and why you should protect yourself from it, but it also curated the developing open source medical designs into a searchable format. And this document was translated into multiple languages. The amount of information that was exchanged and iterated in just March and April of 2020 was absolutely massive. By early April, when the FDA released the EUA for face shield production, US makers had already made 739,000 face shields and 3.25 million globally. This was a direct result of the OSMS call to action. So many of the open source PPE and open source medical designs that you see in your community had some connection to this time in history. Either there's a design still living from that time that is represented in the OSMS project library, or the idea that you could create an open source medical design started during this time. And the expansion we've seen of open source medical hardware has its roots with OSMS in 2020. By late 2020, we ran a community impact survey and documented the global production of 48.3 million units of medical supplies with an estimated replacement value of $271 million. I'm very comfortable saying that that is an undercount because I'm constantly coming across groups that we did not know existed in 2020 who will casually tell me that they made 50,000 masks in Poland. And it's always wonderful meeting the people who were using an open source design and we had no idea what they were doing. In early 2021, we released a comprehensive white paper called Design, Make, Protect, documenting the entire open source PPE and medical supply maker movement, not just in terms of the data of getting stuff to the place, but also the financial, emotional, social, regulatory, and community impact that this made on not just the makers, but the medical professionals they protected. And one of the best ways to really feel the impact of this time in history is to watch a video called Making a Better Now. This is a compilation of clips of organizations within the OSMS community in 2020 documenting all of their manufacturing efforts.
All of our teams are doing everything possible to get as much PPE, personal protective equipment, as we can.
We face an international, a global supply shortage.
Also to protect our tribal members and our most vulnerable population are our elders.
How much PPE do we have for the needs of our healthcare personnel? And they said 10%.
The PPE supply has worsened rather than improved.
In regard to PPE, as you know, there is a market failure.
And I don't want to redo the mayhem of the PPE debacle.
There are times in history when politicians ask for our help. But with businesses closed and people out of work, it seemed like there was nothing we could do. But when you look closer, behind these closed doors and boarded up windows, the human spirit still has a pulse. There are people around the world making a difference. Volunteering their own time and resources, and turning their closed workplaces into PPE factories. We call them makers. Everyday people who were never asked to do anything, but decided to do something. Young and old making and creating masks and shields with 3D printers and sewing machines from bedrooms to factories, from Brazil to France.
Working 24 hours a day, and this is the small workshop.
Makers doing their part as we weather the storm. People from more than 55 countries are volunteering to make millions of protective devices for all of us. They're helping our frontliners fight in this invisible battlefield.
menangani isu COVID-19.
We are finding a purpose in the darkest of times. It's because we can imagine a better future that we are making a better now.
I can never watch that video without getting emotional because I know the names of so many of those people, the names of the organizations in that video. I know how hard they worked, and I know how fast they worked to do good, to try to protect their local healthcare workers. There are so many makers that used their own money to manufacture PPE and then gave it away to so many hospitals and community centers. It was a really phenomenal time in history. And OSMS was there to document it, to celebrate it, to show that this collaboration of individual makers and fabricators, distributed manufacturers, small scale and scaled manufacturers, was a workable solution that if you just helped it a little bit, if you documented it, if you put policy ideas into place, would create a solid infrastructure in your local economy. So our white paper, Design, Make, Protect, is on the OSMS website. You can download it. We have our data here. We also have a one-pager that has a very detailed representation of some highlights. And you'll see here a really interesting graph that not only did the OSMS documented PPE production track the surges of COVID-19 cases in early 2020, but the peak of production occurred before the peak of COVID-19 cases, which means that you had product going out into the community before it was most urgently needed. That is incredible when you think of the fact that there were no PPE, open source PPE designs before March 2020, how fast the community worked, how fast the stakeholder collaboration worked. It was a really incredible time in history. So the open source designs from that time are featured in the OSMS project library, which is a wonderful searchable library. This has been refurbished, or it's about a month old. So feel free to search for designs in here. This is all manually curated. There are no scrapers or bots in this library. And we do participate in the open know-how metadata standard. That's a new effort, but we're very proud to be participants in that. So our vision for the future is to continue truth and access. We want to continue the forward momentum of connecting communities, documenting success, helping our open source ecosystems develop partnerships and innovations that help save lives. Our partners and colleagues that we're very proud to partner with are Public Convention, GLIA, Internet of Production Alliance, Field Ready, Make Magazine, where OSMS has a recurring column, OSHWA, Every Breath Counts, and the free and open source Sustainable Technology Lab in Western University with Dr. Joshua Pierce. Over the years, OSMS has learned that our understanding of crisis response with distributed data and distributed nodes of response ties over well to the humanitarian efforts for disaster relief. So we're very proud to partner with a new humanitarian software platform called SOS, Help the Helper, and also a 501c3 called ConversaCore, which runs a collaborative Slack called Aid Arena. In 2022, OSMS and Public Convention co-founded the Global Open Source Quality Assurance System, which is designed to create and support open source tools which promote quality assurance for basically any community who needs them. Under this umbrella, we have developed a product called Global Distributed Tracking, which is a free, completely open source and encrypted software for documenting information, device provenance, or shipment validation. And I will take you to a video that talks about this.
Every day, humanitarians crisscross the globe delivering life-saving aid. But tracking those vital shipments to the last mile can often prove impossible. Fraud and theft can be widespread with no transparent documentation to light the way. From the open source team that built a new PPE supply chain in 2020 and became NASA contractors in 2022 comes a solution. Our Global Distributed Tracking System, GDT, allows you to track aid deliveries from point of origin to the final recipient. No download, no login, no fee. With a simple scan of a QR code, you can ensure that aid reaches the right person. Because GDT is fully encrypted, documentation is secure and private, even in conflict zones. Now, anyone with a smartphone can verify chain of custody within their humanitarian mission. Global Distributed Tracking. Trust through transparency.
So one may watch that video and ask, well, why do we need another tracker? We have USPS, we have FedEx, we have DHL. And the answer is not every place in the world has that logistics luxury. And we learned from 2020 that while you may have the best open source crisis response, just-in-time distributed manufactured product in the world, because you're making this product in 2 weeks from a valid open source design instead of over the course of 2 years at a manufacturer that has regulatory compliance, it's very difficult to prove the quality, the QA process, the QMS that this manufacturer worked under. So how could we make a free, easy to use tool that will allow the manufacturer of such an open source product to prove the quality? How could we allow a product to be made that a regulatory compliant manufacturer could use for their recall process, for their logistics management process? So we're very excited to have GDT be a tool for our open source medical hardware community. In closing, OSMS, as I've stressed, does not make PPE or medical supplies, and we do not own any designs. We do not make designs of our own. We are instead here to identify problems and solutions and curate data that helps create answers to both of those. We are here to support, elevate, and celebrate all of you that are doing work in the open source hardware world, especially as it relates to medical and humanitarian impact. And as always, we are here to document and to communicate these efforts, not just within the open source community, but externally to stakeholders who support the mission, but may not be formally part of the open source community. All of you inspire us, and we are here to help you achieve your vision and break down silos, create collaboration, and bubble up best practices that may be hiding somewhere that we don't know exist and turn those into actionable steps so that all of us can benefit from the hard work that everyone else is doing. Thank you so much for your time.
Next up is George Fakes and Daniel Lamb. They are medical students and researchers at the University of Texas Medical Branch, where they work at the UTMB Medical Prototyping Lab. Today, George has focused on using 3D printing to fund a toy drive, which has raised over 1,000 toys for pediatric hospital patients and $20,000 for student scholarships in the past 4 years. Daniel Lamb has experience establishing startups and commercializing 4 medical technologies through UTMB's Department of Innovation and has used 3D printing to innovate robotic surgery training in the field of otolaryngology. Give them and their talk, Refining 3D Printed Tungsten Shielding, a Collaborative Approach to Clinical Customization, a warm welcome.
Okay, good morning, everybody. It is so nice to be here. And I would like to thank you, Oshwa, for allowing us to give this presentation to you guys. We're really excited. So basically, my name is Daniel Lamb, if you guys haven't met us before yesterday. And this is my good friend, George Faquez. And we're here to talk to you a little bit about 3D printed tungsten, which is something we're really excited to share with you guys today.
Yeah, so to give a brief overview of what we'll be discussing today, first we're going to be talking about our background, just kind of who we are, how we got into this. Second, we're going to be kind of explaining a little bit about radiation therapy. Third, we're going to be discussing tungsten filament. I don't know, you don't know what that is, but don't want to spoil it too much. And fourth is kind of its inclusion in open source.
Okay, so just to give you guys a little bit of a background about who we are. So George and I are really good friends, and we actually met freshman year of undergrad. We worked on a bunch of different projects together, and we shared a lot of visions together, and so it really just clicked. And since then, we've developed a lot of different things, products, projects, clubs, and we've been working together ever since. And recently we found out, last year, we found out that we got into the same medical school, and so we continued our journey together in medical school.
Yeah, and so this is kind of how we got into 3D printing. So it all started, I guess, for me about 8-9 years ago. I was a sophomore in high school, and I was a book nerd, and I was always in the library, and the librarian was telling me how she had just bought this really cool new thing called a 3D printer. It was maybe less than a foot tall. It could maybe do something that was like 1 by 2 inches. It was really, really small. And I had asked her, I was really big into video games, could I print like a little video game character? And she was like, sure. And it was really bad quality, but it did its job, and it opened my mind to like, wow, this is a really cool technology. I didn't even know this existed, and it was so new at that time. As I got into college and went to graduation, or as I got into college and did undergrad, I was walking in the science labs. I was a bio major, and one of the labs had a lot of different huge moving orange machines. I talked to the lab director there, and I found out those were 3D printers. They were very different than what I remembered them looking like maybe 3 or 4 years ago. And we had one that was literally the size of a closet. I think it was about 4 feet by like 9 feet. It was this huge 3D printer to see how much it changed. And so that really got me into it. You see the photo on y'all's left is a 3D biomolecule microtubule. So that was the first course I took in undergrad about 3D molecules and design. It was about understanding the complex mechanisms of proteins and understanding the 3-dimensional shape and how proteins work together in the human and how their shape really affects that. And so the director was just really, the professor was really involved in 3D printing and wanted to combine that. And so from there, that was my first print I ever did. It was about 1 foot tall, and I designed my own microtubule, finding the dimerization of it, a whole lot of nerd stuff, but I created basically one of the building blocks of life. From there, I really just enjoyed it. I saw the opportunities that could come from 3D printing, and I wanted to maybe do some things for change. One of the things I thought about was maybe designing some 3D printed ornaments. And that was whenever Daniel saw me working on 3D printing. He was asking me what I was doing, and I showed him a little bit what I was doing, and he caught on so quick. He was a natural, And from there, we started making a yearly toy drive. You can see in the middle, this is one of the booths we had. We basically custom designed different ornaments for our university and sold them in exchange for toys. And so within our first year, I think we raised 200 toys. And then from there, we just kept expanding on and concluding and making it bigger and bigger and bigger. And from now, it's been over 4 years. We raised over 1,000 toys for pediatric patients. We raised over $1,000 for Houston women's shelters. And we raised over $20,000 in scholarships for undergrad. Thank you. And we're planning on continuing it again this year with UTMB. And so we're looking forward to continuing that. And then you see on the right, kind of going now into medical school, this is something that Daniel had worked on called DAX, the little robot for pediatric patients with the AI scribes. They don't want to see a little robot, they don't want to see just a phone recording them while the scribe is kind of writing what they're listening to in the patient encounter. So Daniel had come up with the idea of what if they are seeing a robot that they're kind of listening to. And so that's something that Daniel had worked on.
Okay, so as we transitioned into medical school, we really wanted to see how far our 3D printing hobby can kind of take us. And we kind of understood that there was some 3D printing in medicine, but once we got there, we really understood like the true breadth of the things that you could do with 3D printing. So 3D printing in medicine is very, very common, actually. It's been done and implemented at a bunch of different subspecialties around the medical field. And one of the biggest things was that I found out that you could take a CT scan and convert it into a 3D model of the patient or any of their limbs, their bones, their skull, or anything like that, and actually build off of that. So in the field of orthopedics, this is done all the time to create custom implants for patients, like bone implants and things like that. There's a lot of surgical guides that have been invented. And so really, once we got here, we were like, hey, this is something that we can really expand on. There's more to this than meets the eye. And so we really realized that we could take our hobby as far as we wanted to go. And so that's where we discovered kind of a little bit about radiation therapy. Okay, so a little bit of background here. I went and shadowed a doctor for radiation oncology. So they treat patients that get cancer with beam therapy, different types of radiation therapy. And so it was really fascinating to see. Basically, radiation therapy is if a patient comes in with a cancer, whether it's a brain tumor or an intra-abdominal tumor or like a cervical cancer, they can be a candidate for radiation therapy, where you basically have this linear accelerator inside the hospital room, and the patient will sit and they'll get basically a concentrated blast of electron beams into where the tumor is. So the physician will sit there and kind of basically draw out and map out where that tumor is, and then give it to a physicist. And then the physicist will use that and basically give the instructions to the machine to kind of cure cancer in patients using radiation. It's really cool stuff. So to give you guys a little bit of an image, the linear accelerator basically rotates around the patient 360, and then using different shapes, using kind of different materials to adjust the shape of the beam, we can kind of concentrate exactly where we want the beam to be to treat the patient intra-abdominally without having to do surgery for them.
Yeah, and so one of the additions to electron beam therapy that Dana was discussing is something called brachytherapy. It's a form of internal radiation that actually will deliver the targeted radiation seeds directly into the patient. So it's not like they're just shooting beams, they're actually taking small seeds. And it kind of says right here, some of the things they use: iodine, palladium, iridium, some scary names, and they're basically directly injecting it into the patient. And some of the use cases for this is things like prostate cancer, breast cancer, cervical cancer, where it's usually deeper in the body cavities, and they don't want to just do kind of broader radiation or electron radiation. And so the goal of this is to really target just that area without really pushing all the other areas around it to getting more damage. And I know what you're thinking: what is that collateral damage? So a lot of things in medicine are really comparing the benefits versus the risks. And so we can see here for brachytherapy specifically in conjunction with electron beam therapy alone in these specific cancers, it's really beneficial. So currently brachytherapy is used in almost every single case of cervical cancer. The reason why is they see it changes lives. So you can see the numbers on the graph. So when brachytherapy is included, the 3-year disease-free state is 79%. That's a 12% increase. When we're looking at the big numbers, hundreds of thousands of people in the US get electron beam therapy every year, millions in the US, or millions in the world, sorry. And so this 12% increase in saving lives is a big number. And so it's really important that whenever we're doing these things, we're really considering those risks, considering what does it mean to inject someone directly. And like I said, the benefits in this case definitely outweigh the risks, but it's definitely something that's constantly on the physician team's mind.
So in the field of radiation oncology, collateral damage is something that the physicians think about constantly. We are constantly, like George was mentioning, kind of weighing the risks and benefits of the procedure. We don't want to give radiation to patients that don't need it, right? But so there's a whole slew of research in the field of radiation oncology that is working on trying to prevent and block collateral damage for patients. So there have been systems implemented to prevent motion in patients, kind of comfortably keep them in place so that we don't get shifting of the radiation therapy. Or there are different ways we can kind of make the process more consistent for the patient. So, you know, organs inside your body will shift around, right? They're not consistent. So you can create boluses to kind of hold those cavities in place so we can treat the tumor more consistently. And so a lot of the big talk about radiation oncology is how can we prevent additional radiation from reaching parts of the patient that don't need to be reached, right? So we can treat it effectively. We can be more kind of liberal with our treatment as long as we have enough leeway to protect the patients from additional radiation exposure.
Yeah, and when anything involving radiation is involved, usually, I know y'all have recognized this, whenever y'all go to the dentist's office, they put it when you're getting x-rays. It's really important for usually the entire team to be wearing stuff like this. It's basically a shield that you put on top of yourself. It's usually made out of lead, and it basically does exactly that. I know it doesn't really make you feel comfortable whenever the doctor's like, oh, you know, everything's fine, and they start the machine and they run out of the room as quick as they can. And so it doesn't really make that reassuring. But once again, there are things like this that help everyone. And so this is usually, like I said, made of lead. It's usually only placed on top of you. And the reason why they use lead is it's extremely radio absorbent. It helps absorb a lot of that radiation to protect those other organs that we want. And the thing is, that is not specifically a trait with just lead. There are other properties of metals that have that same property. One of those being bronze. Bronze is also pretty radio absorbent. Another one is tungsten. Tungsten is extremely radio absorbent. And the thing that's different than lead is it's not really toxic. Everyone hears about lead poisoning, lead toxicity. So why don't we do something more like that? And the thing is, there's a lot of problems with tungsten. I think y'all probably know this figure a little bit more than I do, preaching to the choir, but CNC machining is one of the big ways that we actually use tungsten to basically get it to the product we want. One, we know how expensive that process is. Two, how hard it is to actually bring this into a direct patient care. There's not really much ways to kind of tie those two together. One, like I said, the process is pretty hard. Usually it's pretty wasteful too. You have this big sheet of tungsten, and basically in these huge CNC machining, you're basically having to sculpt out the product you want. So you're losing a lot of that actual raw material, first of all. And two, the customization, one, really isn't there. It's huge machining. Like I said, processing cost isn't there. But if only there was kind of a way that, you know, how can we manufacture this a little bit better?
So this is where we kind of want to talk about the new kid on the block. This is some really exciting stuff that was developed a few years ago. And it's a tungsten polymer hybrid. So there's this company called Prusa, you guys have probably heard of them, that developed this polymer that has tungsten powder embedded into PETG. So it's 75% tungsten by weight, and it shares a lot of properties that tungsten has, but also has the manufacturing ease of 3D printing, like a normal thermoplastic. And originally this product was developed for nuclear pharmacy, where, you know, it's really, they need to develop like pharmacies that compound chemicals for chemotherapy. It's actually really dangerous to manufacture and ship those products to hospitals worldwide. So one of the things that Prusa came up with was, hey, let's find a way to easily create custom packaging for nuclear pharmacists to be able to make their medicine and ship it easier to hospitals. So we wanted to take that idea and kind of convert it into the field of radiation oncology, where, hey, custom face shields, custom implants for patients to protect them from radiation therapy. This is a really, really good use case for something like this. So let's look at the actual attenuation of performance of something like this. So it's, you know, some made of plastic. So how much better is it? How good is it at blocking radiation? So actually, the red graph here is the radiation attenuation performance of this tungsten filament by thickness. So once you approach 1 centimeter of thickness, it becomes just as radiation opaque as tungsten and lead. So this means that you can create very clinically viable shields that are only a centimeter thick that has just the same level of performance as something like a full sheet or block of tungsten or lead.
So cost of production, we know, especially in something like healthcare, cost of production is a very big factor, especially if we want implementation into things like hospitals, things like that. They definitely want to be looking at these numbers. And so is it actually cheaper to be doing this? And so one, we're looking at the left graph, we see the material cost. The material cost of tungsten is around $240 per kilogram, while the material cost of the polymer, the filament, the tungsten filament, is around $230. The thing is though, two things. One, sometimes those costs can kind of vary, so we're going to kind of give that an equal thing. But the thing about the tungsten CNC machining is, like I mentioned before, it's extremely wasteful. You have to start with this huge block and bring it down and kind of sculpt it. So sometimes you're not even using 100% of that block. You're maybe only using 40, 50% of that block to get that desired product you want. Compared to 3D printing, most of y'all know how we kind of build it from the ground up. It's extremely wasteless when it comes to the actual material to the product. And if there is some waste, it's usually going to be in a kind of form of support material. And the good thing about 3D printers now is you can actually change what that support material is to maybe use it something like a cheaper material for the support. And so you're only using that $230 kilogram, the expensive PETG, for the actual product you want. And the most important thing in this case is going to be the production cost. So about an hour cost of CNC machining is about $100 per hour. And if you were to go to a 3D print farm, it'd be about $20 an hour. But most of us don't use 3D print farms anymore. Most of us have it at our homes or at the universities or at hospitals. And so in reality, it's usually a one-time cost. And this is maybe Gen Z math, but after that, that means it's basically free. So every single time after that, you're not really using material costs for actual processing. And so from that, all you're really using is the material cost of that $230 per kilogram, and you don't have to worry about this constant CNC machining fees. So really cool uses.
Okay, so the really cool thing is that the printing process is basically the same as every other thermoplastic printing that you would want to do. The only difference is that you would have to change the nozzle in your printer to a hardened steel nozzle. That is a fairly common upgrade that you make for most 3D printers. But other than that, that means you can use and print tungsten filament at home with proper ventilation, of course. But, you know, this is way better than you trying to machine your own like tungsten, I don't know, like shield from home.
Yeah, so safety and quality considerations. Because this is a more newer filament, there isn't too much research on it in general. But what we have to do is kind of break it up. So like Daniel was saying, it's a combination of PETG and a combination of tungsten alloy. So innately, both of those are biocompatible. They don't cause any toxicity. And the thing is, whenever they actually created this product, the combination filament, there wasn't really any chemical changes. It was just physical changes. And so we hypothesized that there shouldn't really be any innately different biocompatibility. And so there isn't a direct biocompatible label on it yet, but there isn't not one. So that's why we're just saying this is maybe something that we need to look forward to and research. And is it actually biocompatible? And based on the science, it should be. And so how can we use this in healthcare? And some of this is like kind of what Daniel mentioned, 3D printed tungsten shields. A lot of the things of radiation therapy that we talked about is collateral damage. So what if we combine that with something like tungsten? You're not using lead anymore, so it doesn't have to necessarily be on the outside of the skin. And there's a way that you can 3D print it to be customized per patient. So like in this case, you're literally just putting it on top of a patient. You can customize their face and be able to reverse engineer it and literally make a custom shield. Another thing was the whole brachytherapy I mentioned before. If we're doing something around the cervical area, there's a lot of important parts around there, and there's a lot of risks that come with directly putting radiation there. You have your genitourinary area, just kind of your rectum is right behind. You have all your reproductive organs there. And so do we really want to be blasting radiation surrounding that area? So if we can custom make a shield for those areas to make sure whenever we're putting this radiation inside a patient, it's not kind of going out and blasting all of its surrounding areas. And so how do we maybe do that?
So let's go through a little bit of the clinical workflow of how you'd be able to implement something like this for patient care. So whenever a patient comes in and they have a cancer, we kind of analyze them to see if they're a good fit for radiation therapy. And if they are, they're sent to get a CT scan. So that CT scan is already done for this radiation therapy anyways. What we can do is we can actually take that CT scan and then put it in a program called 3D Slicer. 3D Slicer is the program I mentioned to you guys before, where we can convert patient CT scans and DICOM information into 3D models that we can build off of. And so from there, we work with the physician in order to build and custom print a shield based off of the patient anatomy and based off of where that tumor is and what we want to protect. And so we use generic CAD files, CAD modeling, and use a readily available free program on 3D Slicer to be able to implement something like this for patient care. And so there's another study that has been done, not by us, but by a different institution, and they did the same workflow, but instead of using tungsten, they used bronze. So the images I showed you in the last slide were with bronze filament. So they took a CT scan of a patient and they custom fit bronze shields for the patient, and it actually showed that they achieved a 95% dose reduction and improved fit and comfort. The good thing is that this workflow, because it's 3D printed, is easily adaptable to the tungsten filament. We literally just swap the filament, the printer stays the same, the workflow stays the same, and the process stays the same. And so we can actually create a much higher efficacy of radiation attenuation with very little modifications to an already existing workflow. Oh, yeah. And so I wanted to talk a little bit more about like how this all ties into the open source thing. And I know we talked a lot about 3D printing and open source yesterday. But the nature of 3D printing is inherently open source. Whenever George and I got into 3D printing, we used Thingiverse, MakerWorld. These are all readily available websites that allow you to take and modify designs for free online. We really used this to we took it really far. But basically, what I'm trying to say here is that this means that the distribution of files and the distribution of the workflow is really easy. We can transfer this information to hospitals and implement this to a wide set of patients much quicker than if we had to develop like a CNC.
Patient. That's something that I think, take that privilege really highly. And it really is an honor in this kind of innovation team working together with engineers and collaborators of actually being the ones to speak to the patient. We are seeing them before they go into these therapies, during the therapies, and after, making sure that everything is staying good, making sure that we bear that responsibility of keeping up with that patient. And so it really is about this collaboration effect, this innovation team that works together. And I think this presentation is kind of a tribute to that. The engineers at Prusa did their jobs. They found this really, really cool, broad, useful 3D printed tungsten filament. They didn't really give a specific use for it yet. And so it's our jobs as future physicians, seeing these patterns, seeing how can we make a change and connecting those dots. So it's really that intersection that we as a team need to work together to really make an impact, figure out that concern, and find the solutions together. So thank you all very much. We appreciate all of y'all. Thank you. Thank you.
God, I love Gen Z. All right, next up is Enrico Bassi. Enrico is a designer, maker, and innovation consultant. He managed Fab Lab Italia, the first Italian Fab Lab. Fab Lab Torino, supported by Arduino, and OpenDot, founded by Design Studio .IT. He is a professor of digital fabrication and participated in projects and lectures in more than 35 countries in the world. Give him and his talk, Beyond Medical Devices, What Communities Have Done Around the World, a warm welcome.
Hello, everyone. It's a pleasure to be here. Thanks for the introduction. Thanks for the invitation. It already helps me to skip the first slide and jump to the second. So even if I'm a designer by training, I basically immediately moved into innovation and somehow open or openness without giving it a definitions, thanks mainly to these three people that you might recognize. So Neil Gershenfeld, the founder of the first Fab Lab in MIT, Massimo Banzi, co-founder of Arduino, that also supported the work we did in Italy. He was a huge help there. And Adrian Boyer, the professor that created the first open source 3D printer. So these people somehow lay down the foundations of what I worked on. And it was a long journey that included many things. A huge part was about healthcare somehow, but we define it health and care because actually the first thing I worked on in 2014 was a fork that helped people to roll spaghetti properly. In Italy, it's a big issue, of course. So this gave me the opportunity, thanks to an association that I helped starting called Hackability, to understand that people might get a huge boost in their daily quality of life just because of simple objects sometimes. We started in 2014. Back then I was in Fab Lab Torino in Turin. But the project went on and my interest in health and care went on. And it brought me to two main projects that are the two things I'd like to talk about. The first one is Careable. This is a project started thanks to a European grant. So we got public money to understand how to help people to create their own solutions, but also how to share them. This started in 2017, officially at the beginning of 2018. So it was a while ago. Careable is actually a collection of documentations. We spent a lot of time figuring out how to help people to document. Everybody needs documentations. Nobody likes to do it. So how can we make it a bit easier? And a lot of the conversations was on, okay, let's figure out templates. Let's help out with licensing. That it's such a complex things nobody fully understand. And we needed a license for the documentations because that goes in more in the Creative Commons area. And we need a license for the hardware because that's a different things. And software has a different license too. So it was a bit of figuring out the complexity of the word. We worked on creating a template, again, that supported people. The idea was to make things homogeneous. Andrew didn't came up yet with his standards on documentations, so we had to think about it in this way at the beginning. Again, step by step, and we ended up having more than 100 projects on the platform. We figured out that nobody wants to move to your platform. Everybody's comfortable in their own home. So if they start things from scratch, then it's good to give them tools. If they don't want to document things from scratch, let's not force them to redo things or to maintain projects on different platforms. So the point was, how can we at least summarize things and have a sort of directory of projects and idea, and then everybody will go on with their own platform and way of documenting things. This is a bit of a bittersweet story because, as you might know, maintaining a platform is tricky, and at the moment, the things you see here are not online anymore. We are trying to figure out a new home where to move them, but the material is still there, so nothing got lost. It's just not available at the moment. The second project that was somehow coming out of this, and it was a sort of second side of Careable, is FabCare. FabCare has been started by a group of people, mainly 2 labs in Europe. One is OpenDot, that is the lab I used to manage, and the second one is FabLab Camp Limford in Germany. It's still an active group. The idea of FabCare was, let's define what we believe in and see if there are people believing in the same things, so we can do a piece of the path together and walk together. It turned out that there's a lot of people interested in what we were interested in. And we thought about how to help people to navigate this health and care world. We figured out that you can do basically 10 different things in the field, starting from very simple one to very complex one. This was a way for us to explain to people to don't jump straight into the tough stuff if you haven't, let's say, explored easier things. Each step you find on the platform is described with a bit of examples. Many of the examples you see here comes from things you heard about during these 2 days, and I'm very happy about it. For instance, when you start to replicate, it's good to know that there are many platforms, again, that collected open, maybe not fully open, but documented health and care projects. And we listed like 50 existing platforms. So the point is more, how can we merge them together or connect them together more than start the 51st? Some are very active, some a bit less, and that's another thing. How can we keep things rolling? The second part is about how to involve people. Again, I'm a designer as a background, so to me, the key point is the design process, in a sense of starting from a real need, from a real category of people, and find an effective solution for that. So the key approach that we used is participatory design or co-design. And we shared all the documents that we were using during the processes. Sometimes people don't understand that they are not, how to say, when they interview users are a bit too direct. That could be offensive, or you're speaking about a very sensitive topic. So even giving suggestions on how to run an interview was important. We did innovation process with doctors, help them to collect the daily problems that they were facing, the daily needs that they had was the starting point and catalyst to think about innovative projects. So the community at the moment is growing. Every time we do events and activities, we ask people if they want to join the group. The way we communicate at the moment is a simple WhatsApp group. Might not be the best tool, but is very widely used around the world. So it's a good compromise. At the moment, there's like 150 people in the group, in the chat from around the world. I tried yesterday to check out a bit of the nations, and after a while I gave up, but I was up to 30 more or less. So it's a nice group. If you want to join it, feel free to do so. We are happy to welcome people. We also want to use the group as a way to put in contact people that are working on similar things. I will get to this towards the end of the presentation. There are topics that are recurrent, and people really struggle to cooperate, and I will get to that as well. So the community, again, is wide. I will give you just some example. This is Marcela, a recently graduated student from Peru, and her project was a way to learn and to train for Braille. So she developed the entire project, the software, the hardware, and everything is published online. Sonoko from Japan, she is the manager of a Fab Lab Shinagawa, that since day one worked a lot on occupational therapy. We got the chance to do a project together in Bhutan a few years ago. Everything is properly documented in Japanese, but nowadays not such a big deal anymore. So it's a great example of a place that focused on a specific topic and from healthcare professionals, or from an occupational therapist. Another amazing human being that many people in this room might know is Saad from Savage Garden. It's a beautiful place inside the library in Shanghai. No, sorry. Oh God, it will come back to my mind. I'm sorry, Saad. Anyway, so the lab is actually open once a week. The idea is to base everything on volunteering, and they gather together and create a solution for a person per week. They work on few projects at a time, but they are very consistent. So it's a very, very nice approach. I love the term healthware, because for many years we were thinking, how can we define everything that is an object or a piece of software, but there's something as a product there that is connected to health and care. And we tried with the term careable, thinking about instructables connected to the idea of documenting things, but it wasn't clear. While I think that healthcare, even if it might sound a bit technical, it's a great definitions. And this is what I've seen personally could fit inside that. It's my opinions, of course, so I'm happy to talk about it. First of all, simple assistive devices, object that might help you to grab a pen and write. Glypho is a beautiful project started with a foundation in Milan called TOG. They do therapy for free for more than 100 kids with complex neurological disease, amazing human beings. This has been developed together with Open Dot, the former lab I was managing. And the interesting thing is that there is an entire customization process you do online. So the parents of the kids can follow instructions, take pictures, figuring out the right angle, personalize the object, and get what they need. Again, the key point here is not 3D printing a way to hold a pen. We have 1,000 of those, but it's to empower people to be independent in the process. Again, another project done with this TOG Foundation. This was a postural seat for one of their kids. It was meant to allow this girl to actually touch the ground and walk around a bit using the limited mobility she had, holding the right position. But the interesting thing is that it was very respectful of the process they have to work on things, because they use the Metayer method that is based on creating plasters by hand, custom made on the kid need, that is of course the posture, the limited mobilities that they have, and so on. And to them it's important to do things by hand, because you cannot 3D scan the body and modify that. You will not have the sensitivity to feel the proper positions, the tensions in the joints, and so on. So we kept the same process. We just digitalized the cast that they make, modified slightly to be printed with a larger printer, and create custom solutions like this. Another great field is the medical trainers. We've seen some examples yesterday. Few years ago, the Apropedia platform ran a project together with many partners. One that was actually supporting economically the project was the Intuitive Foundation, and the objective was to design and share open medical trainers. Now, personally, I believe that medical trainers are a great fit in the healthware category, because it's such an impactful tool, in particular in some areas. And sometimes it's very easy to make it. So when we calculate somehow the impact over costs, it's a very advantageous thing. I don't know why as an Italian I jump in complex English words, but forgive me for that. So medical trainers, again, fundamental thing. Now Apropedia is working on a new project. I don't know how much I can say about it, but we worked together on that, that it's connected on its sort of next step. That would be an open database of tools in this direction. Rehabilitation and training, huge field. This was during COVID. The rehabilitation process was interrupted because kids could not leave their own room to go to the gym in the hospital. So together with a local hospital in Milan, we developed again, when I was in Open Dot, this training kit that you've seen. Every piece can be assembled, disassembled, scaled, moved. Everything can be handled by a single person and so on, and everything was designed on the needs of the therapists. So doing therapy for some conditions is fundamental, is the only way to mitigate the problems of those conditions. So supporting a customized therapy is incredibly impactful. Oh, okay. I'm not sure why, but that's okay, I can move forward. So limiting the capability of students to actually learn things has a long life impact, of course. So when the disabilities or the health conditions impacts kids, the consequences might be worse. This project is a super nice project. I'm very proud to have been part of this. It was a few years ago in Bhutan. Bhutan has a set of schools for students with special needs, but they had no program to, let's say, create projects, create objects that supports the students. So we spent a week together there. Our objective was to empower the local students to learn how to create the solutions, figuring out where to find existing products again. You've seen Sonoko, how to repair with the local tools the existing aid. We created Braille printer. That is an open project. Again, Sad was working on this. We created simple communication boards. We created custom-made soles for the kids. So it was really about exploring different aspects and do a one-to-one project. The interesting thing is that recently I saw that the project is going on, so it means that it was effective. And again, the idea was to create a STEM program for the university students. We gave them a plan on how to move forward. Apparently, it worked well. Besides being a maker and a designer, I'm a visiting professor in different universities, and I figured out over the years that for many students that might not be passionate about technology per se, Healthware is a great way of engaging them. You give them a reason why we should do what we do. So over the years, I asked my students to design things that they find useful for someone they know. And every year is a surprise. This was a couple of years ago. A group developed a sort of transportable fridge for insulin because one student had a younger brother with diabetes, and it was a limitations on how long he could travel because he need to keep the insulin pen cold. So they basically hacked a thermos cup, I guess it's the name, and sensing the temperature inside, activating a Peltier cell to reduce the temperature, use an external power source, and that was a simple project, but very effective. Another nice one was to motivate kids with arthritis that sometimes hits in the younger age to do therapy. So they transformed the controller for video games into a glove that check if you're doing your exercises for the articulations of the hands and everything. And if you do it properly, the games goes on. Otherwise, it stops. It was a way to push kids to do boring movements for hours a day. I think it's useful because of two different things. You got the output of the product that might be a brilliant idea and you might want to bring it on, but you also got the outcome of the learning and the empowering of the people that you work with. Very often disability is invisible, in particular in some cases. So you might want to create kits that can help people to see things that might not be visible. Again, arthritis gives you pain that is not visible sometimes. So experiencing the same conditions helps to create empathy. And this was for the National Associations of People with Arthritis. Another nice example is that big projects like ventilators might have consumables that are harder to get. So you might get in some remote areas big machines that then stops to work because you end up without pipes, or in this case without nasal cannulas. This project was done by the Polytechnic of Milan. They developed a low-cost oxygen concentrator, and we helped them, again, with a team of students to create a local production or a way to produce locally hundreds and hundreds of reusable nasal cannulas for babies. So this is the final results. I'm sorry for the quality of the video, but this is really ongoing now, so I picked up the last version. You can 3D print the mold, inject it with a syringe, 3D print a part that holds that. Everything is disassemblable, so you can disinfect it and reuse it. Now, it's a super small object, super cheap one as well, but it might be the thing helping the machine go on longer. Sometimes you get the money for the machine because of donations, but you don't get the money for consumables. So you have to be creative on that. Okay, closing up. I noticed over the year that some topics are recurrent. So one of the things that seems to pop up more and more and more and more are prosthetics. But everybody seems to start from scratch. This was a project that we did in Bali. In Bali, there were already 3D printing experts and professors that knew how to 3D print on one hand and design on the other. But there was no system in place. So the dots, the ingredients were there, but they were not connected. What we figured out was a way to connect the pieces to create a sort of ecosystem. Amputations are unfortunately very common in Bali, mainly because of traffic accidents. So it's something that is needed, but there's no good solution in place. So starting from existing open projects, the students were learning how to use the machines, cooperating with the doctors in the local center to take the measurements of the patients, sending back to the main universities that were collaborating on the projects the dimensions. They were customizing the file, send the file back locally. The local team was printing the pieces and bringing it to the center. So again, the idea of how to create the system more than thinking about new technical things. This was basically the tools that we ended up making. Another nice lab in the network is working on similar things. These people are in Amman, and you might know why it's needed at the moment to focus on oh, that's a pity though, on prosthetics. I'm sorry about the pictures, I don't know why, but you can see one girl from Gaza actually to test out her new prosthetics. And again, the hardware there, it's super simple. The solution exists, but you have to create the systems and foster collaborations. So closing up, this is my personal opinion. During the last FAB event that happened less than a month ago, both Prusa and Banzi were saying that open hardware is not doing well. They were speaking about it in different situations, in different interviews, so it wasn't like one impacted the other. They were basically saying that some of the collaboration mechanisms that we were hoping for are not fully working. Many people don't contribute on open hardware, and open hardware is very different from open software, of course. So the rules are different, the way to distribute things is different, managing the versions is different. So it's a thing to think about. And if I should think about why, in my opinion, we should use open hardware, or what's my why for the open hardware, I think that it's a way to provide a solution to the need of people in some context at least. But it's also a way to give jobs to some of the people close to the people that need something. So start to decentralize this idea that the best way of producing a solution and distributing a solution is a big factory with high production capabilities. And when you think about that, then patents becomes a tool of the past, at least in this specific context, because it was created to give time to factories to scale up production. So open hardware, in particular, open healthware, might be an opportunity to think about a new model where production ideas, solutions start again from the local needs. Creating local jobs and distributing the production also means to create something that is more resilient to change. If someone drops out of the production, it's not impacting the entire supply chain. If someone change career, is not such a big deal. If some countries has regulations that stop something, the others can go on, and so on. So it might be an answer to the complexity that we are facing. The last point is to facilitate collaborations. Many research centers, many universities needs problem to work on. It's actually a way to, again, engage students, bring on research while in other places you might not have the resources to do those experiments. So figuring out also collaboration models might be interesting in that direction. So this is my hope. This could be an opportunity to think about maybe even something that is not necessary open source the way we imagined it or the way we are used to, but it's a tool that starts from a different need. So if patents started as an answer to the problem of giving factories time to scale up production, and open source as a reaction to the closeness of that system, open source is a reaction to a system that is not what we want anymore. So somehow, maybe open source started not as what we need. If you think about the beginning of internet, it started as a way to communicate between researchers. It didn't start as an international tool of collaboration or communication. And we pay the cost of that naive approach today, thinking about how difficult it is to create safe communications or certified communications or verified sources. It's because it wasn't there by design. So if we think as Open Healthware as a new way to create a collaboration platform that is based on rules, that is based on licensing, that is based on exchange tools, it might end up to be different from what we imagine as open source today. And that would be great, in my opinion. Thank you very much.
We're going to start lunch, and we'll just be back in this room at 1. If you have a device that you brought and you just want to show and tell, share it, there's tables set up outside. You're more than welcome to do that. Please exchange business cards. Something that always comes up during these sessions and conferences is that people really want to connect with each other, so don't be shy. Make sure you pass it around. There's a lot of awesome people in this room. Come back here at 1.
All right. Thank you for that quick break. So now we're going to start our afternoon session of talks with Dr. Aysen Kero Chassin. She is the assistant professor of pathology at UTMB and director of the Medical Prototyping Lab, where she engineers a range of innovative devices that directly impact patient care. Her work integrates biomedical engineering with sensory augmentation, resuscitation technology, and surgical stimulation, advancing the field of medical device design. And the talk that they will be presenting is Medical Prototyping at the Bedside, Transforming the Process and Access of Medical Innovation.
Hello, everybody. How are you feeling post-prandial talk? So hopefully you're not passing out and you have more the less not hungry judge effect, which means you'll judge me favorably. If you don't know what that is, Google it. It's fun. So today I'm going to talk about medical prototyping at the bedside, transforming the process of access of medical ingenuity. I changed this last night because I thought innovation has this connotation of newness and more like patent oriented, right? Trying to, do the most innovative, the newest. But I thought ingenuity is better because it's about the quality of being clever, original, inventive, and not necessarily so stuck in being new. So I want to thank you so very much, OSHA. It's been incredible. NSF funding this is definitely an incredible use of our funds as Americans, and Cornell Tech for hosting, and all of your staff that's helped us today, and for leading this historic moment, the first Open Healthware Conference. And all of you beautiful minds who dared to dream of a free and open world for knowledge seeking and sharing. Thank you, you brave reverse engineers for the public good. My name is Dr. Aysen Kero Chassin, and I run the Medical Prototyping Lab at the University of Texas Medical Branch. And I'm also assistant professor of research in the Department of Pathology in John Seeley School of Medicine. And I'm so excited that we are here in Roosevelt Island. I've learned so much about New York, about American history. I'm actually terrible at history, not my forte, but I found this lab, and it apparently is the first institution in the nation for pathological and bacteriological research. Is just down there. You can take a walk at any time. And that stuck with me because pathology is my home in medicine. And so I read a little bit more about Roosevelt, and I found that he actually had kind of a sickly life and had a lot of health issues in his family as well. And his dad told him, Theodore, you have the mind, but you don't have the body. And without the help of the body, the mind cannot go as far as it should. I'm giving you the tools, but it's up to you to make your own body. And so he responded, I will make my body. And so this reminds me of a quote that I actually always use in my presentations because it kind of distills my domain, which is the human-computer integration world, which says, with every tool, man is perfecting his own organs, whether motor or sensory, or is removing the limits of their functioning. And so I highlight perfecting here because I think perfecting is not just a matter of engineering or science, and it's actually philosophy, right? There's bias in perfection. There's considerations beyond faster, braver, stronger. And my work oscillates between art and science. And these are two cultures that are really kind of blended in by experimentation. I chose to start with sculpture as my undergrad. So I started with art because it was just a place where I could be free to experiment, not have any protocols or give any answers, just simply learn creatively and try to understand perception. As an artist, I was really interested to kind of push the threshold of aesthetics. So perception is the limit of our aesthetics. So if I start making new senses or sensory perceptual pathways, then maybe I can make some really new art. And so looking around the internet, like we all do, open source hardware people, in 2011, as I was graduating from my undergrad in Houston, I found that you could remote control people. And so I was really excited about that. And so I made a galvanic vestibular stimulator, which is a mouthful of words, as you can see. Vestibular system is the system that keeps your balance, and it's in your inner ear. You have 3 semicircular canals that are filled with fluid, and they have cilia, this little metalhead rock star hairs that tell your head where it is in relation to gravity. And it turns out that if you use 1 milliamp on your mastoid bones, you put 2 electrodes and you pass them through, you're able to incite these hairs into moving in that direction. So I hacked a remote control car, put this galvanic vestibular stimulator circuit on it with the Austin hackerspace. Back in the day when they used to be called hackerspaces, you know, I kind of don't prefer the word maker as an artist engineer, reverse engineer. But here I'll show you how it works. So this is me in 2011. As you can see, he has a car hanging and he has these electrodes, and you'll see my thumb moving, and then you'll see that he starts veering into the direction that I am controlling him to. So the way that's the tree is, you know, I cannot bypass physical reality like that. But anyway, so so it worked. He has to close his eyes because, you know, like any perceptual information, it's kind of a conglomeration of senses. And so you have your sight and you have the vestibular system. And so when you close your eyes, then you're really relying on the vestibular system to give you information about where you are in relation to gravity. And so when you're closing your eyes, as you see, he kind of reached out. That means that he feels like gravity is shifting from under him. So he's going to start overcompensating. And that's why he starts walking the other direction. So it's kind of an illusion, but it works. We actually use some galvanic vestibular stimulation for aerospace because the vestibular system with no gravity obviously goes berserk. And then I went to Parsons, where I kind of had this idea from Houston, Dirty South rap, the grills, you know these, right? And so I thought, you know, this is like an arbitrary music object, but it has nothing to do with music, but it's wearable technology. And I had just gone to the Exploratorium in San Francisco and learned that you can hear through your teeth, through bone conduction. And so I made this MP3 player grill, and so kind of mixing rap and science and assistive technology. And then I started looking into research, and I learned about that you can see through your tongue. And so this is an electrovisual experience through your tongue is a matrix of electrodes. And it was invented by Dr. Paul Bacurita, but a few artists had come up with it. And I mean, how brilliant is it that you can make art to see with your tongue? And so I actually was looking around and I found this guy, Zach Hoken Smith. And I said, hey, I found your mouth brain. Everybody puts their own name on it. And I was wondering if you could meet with me because I really didn't understand what's going on. You know, I didn't really have a background in electronics at all. And it turns out, he says, oh yeah, I'm in Shenzhen because I started MakerBot. And so it turns out that I was working with the starter of MakerBot, who, I don't know if you guys know MakerBot. I'm sure you do. These 3D printers that kind of started this whole revolution thing. I mean, making it marketing, great marketing. But, you know, they sold Tool to Maker for 400 million. So, you know, for the people who aren't sure if open source is a great place to do business, look again. So this is Paul Bacurita. He's the father of sensory substitution, and he invented the tongue display unit. As you can see here, he invented it for blind people so that it turns an image of a camera into black and turns that black and white matrix into electric pulses. And so it's like a black and white image. Have you ever licked a 9-volt battery? So every pixel is like a 9-volt battery. I'm sure you guys in this crowd for sure. And then he used it for somebody who had vertigo and had lost their sense of balance, and put an accelerometer in a hat and then displayed the information of, you know, the accelerometer and gyroscope. And she would wear it and her body started learning or rewiring somehow. And then it turned to a point where she could wear it for 10 minutes, and then she would go 3 months without having to wear the aid and not having vertigo. And in Parsons, I also met Joel Murphy and Yuri Gitman, who are both here, incredibly so. And they've been my mentors of physical computing. They taught me how to program microcontrollers, and because I had just had some basic hardware experience. And you can see, I don't know what he's explaining here, but that's Joel and I. Huh? Yeah, something like, who knows? And they invented the pulse sensor together, which, you know, it's kind of the basis of open healthware in a way. I remember when I taught physical computing, how many people were interested in using the pulse sensor. And it was just kind of part of the response of this biometric data becoming part of, you know, the user experience in common electronics. You know, Fitbit was also starting to get popular at that time. And then we actually shared a studio space in the Pfizer building, Joel and I. I rented a bench from him, and then that's when he started developing the open BCI. And so that was my first shot at modeling. I was a brainwave model. My alpha is really great. And interestingly, I'm working with it again. So really my work falls in between bioart, device art, and kind of a reverse way of biomedical engineering. So for those of you who don't know bioart, this is Stellark. He's also done a lot of robotics, and this is his third ear on arm. And he implanted a cartilage ear on, well, not himself, he had a surgeon collaborate with him. And he also had implanted a microphone because he wanted to hear through that ear. So when artists do medicine and bioart, you know, it doesn't necessarily diagnose or treat. It's more thinking about the body's plasticity in general. And he told me it's such a pain to go through security when they pat you down. It's like, what is that, sir? What's going on? And then for device art and bioart, here's a Iborg, Bob Spence. He was a documentary filmmaker who had an accident and lost one of his eyes, and worked with Dr. Ling in Scotland and made this camera for his eye. Obviously, it's not a digital camera because an analog to digital converter is too big. And so it's an analog camera, and it passes the signal through radio. And he filmed the first documentary from the first eye perspective. And so this made me question the phenomena of electric enhancement to the body may make some forms of disability desirable. You know, sometimes you look at people with glasses, and I'm a fan of glasses. I love glasses. I wish I was blinder so I could wear glasses all the time, you know? So questioning this, how we are co-adapting with our machines, we are, like Sigmund Freud said, you know, building and removing the limits of our functioning. So now I'm at the Medical Prototyping Lab, which is a space for interdisciplinary collaboration, materializing ideas, conducting research across medical sciences and practice at the University of Texas Medical Branch. And this is my lab. I'm so proud of all my students here. Look at them. I can't wait until they graduate to be my doctors. You know, I'm gonna have so many good doctors. Thank you for coming and supporting me in this journey, guys. And this is all the work that we're presenting to you today. Thank you, OSHA, again. Couldn't be possible without you. And so what is UTMB? UTMB is the birthplace of Texas medicine. We were founded in 1891, which is 1 year after the first pathology lab, which is like, oh, wow, there wasn't pathology back then. Interesting. Well, you know, you live, you learn. And this is the Old Red Medical Museum nowadays, where we have some human specimen collections and other things. and it's kind of being built. And in 2015, nurses had this great vision and put in the first medical makerspace inside of a hospital in the US. Obviously, these nurses are not from 2015. But these nurses are. So it was Dr. David Marshall, who was the chief nursing officer at the time, and Dr. Tammy Cupid, the director of nursing science innovation. So incredibly so was the nurses who brought this kind of space to the hospital, because they have something called workarounds. So nurses are very well versed in having to MacGyver things at the bedside, and they call these things workarounds. And so there was a group of MIT researchers, Jose Gomez Marquez and Anna Young, who co-founded Maker Health, which was a company that was studying making at the bedside. And they did a few studies in Guatemala and then brought it to the Texas Medical Center, trying to find a home for their research and do the research again here in the US. And Dr. David Marshall was super happy to oblige, which then turned into the first makerspace. So the space was really founded by nurses, and nurses use them. And this is Meredith. She's the original maker nurse. And she's leaving, so we copied her. And I'll be printing her next week so that all of her colleagues can have a piece of her. I have my ex-boss there too. I'm thinking of turning her into like an 8-ball so that I can still ask her questions, you know? I miss her. And so this is the lab when it was first founded. It totally doesn't look this clean and organized now, so I keep using that photo. But this was funded by the Robert Wood Johnson Foundation, and it was seminal for all of us. So, and I have the luck and fortune to run this space now. So we serve all of UTMB, even though it was put together by all nurses, clinicians of pathology, ophthalmology, and anesthesiology. We have lots of schools, medicine, health professions, nursing, and graduate biomedical sciences. We also have the Galveston National Lab. We also have the biocontainment unit for that area. We also have the TDCJ, which is Hospital Galveston. We see all the prison inmates from Texas. So, we also have jail in there. And we have a translational intensive care unit, molecular genomics, etc. So I collaborate with everyone there. We also have collaborations outside. We're currently working with the Sasakawa International Space Center of Architecture at U of H. And we took this new model of an EVA, which is an extravehicular activity suit from that Axiom Space is designing for NASA, and studying a framework for virtual reality. And so we took this device with the OpenBCI, and I'm not sure what brand of monitors for VR those are, but we took it on a parabolic flight, and our idea is to try to test all this biometric technology in CROG and see how we can incorporate it into EVA suits. And so, yeah, so what do? We do prototyping. Maybe some of you guys have read this paper, and if you haven't, I really recommend it because it explains kind of like what we do as developers of technology and designers. So it's what do prototypes prototype? And so it explains how a prototype can have 3 different factions: the implementation, which is the technical aspect; the role, which is how it fits within, you know, your user life experience or whatever it is; and then the look and feel, which sometimes in industry is called vaporware. And yeah, have you ever been to like a car show and you're like, that's my dream car, when are they making it? Never, because it's just a shell. You know, this kind of thing where the prototype looks and feels like it is, but it doesn't have any function. And then finally, an fully integrated prototype kind of has all of these together. So this is the map that I've managed to make about prototyping at UTMB specifically, but maybe it's applicable to all institutions that do clinical research. So first you start with
discovery, R&D, you do a prototype and you do some preclinical testing. From there are 3 different offices that we can talk to specifically in our university, the OTT, which will decide whether it's going to be open source or they're going to patent it or they're going to put a provisional and then maybe release it. And then, of course, the famous IRB and FDA. And so within all of that, eventually after enough clinical trials, as we saw in Alex's presentation earlier, you can finally publish and disseminate and hopefully get something to market. But as you can see, it's a very cumbersome space. So a lot can be done at the prototyping stage for research. So we also do a lot of simulation models, like some of the students talked about. We do a lot of 3D printing of CT scans for surgery planning. We also have done simulation surgeries. This is a cholecystectomy model, and it's a liver gallbladder model. And so to learn, you have to cut the omentum, and so that's that kind of sheet that you see there. And then you can extract the gallbladder, and then you can clip it, and so on. So they need to practice this, right? We want doctors to practice on non-living things. So simulation's really good. These models usually cost around $200, and so it's really prohibitive for medical students to buy enough to get the practice they need. And so we remade it, made it 80% cheaper, and made some of the parts reusable, published a protocol and how to maintain it. We also do ultrasound simulation models. This is a ultrasound guided PIV simulation model I did with a nurse. As you can see, we were trying to make a simulation so that nurses can learn how to insert IVs with ultrasound, so you can learn how to see ultrasound. Like, there's a baby in there. No, I'm kidding, there isn't, but Yeah, and so I've been trying to learn how to make visuals for sound to see. And so also taking the opportunity to make them beautiful as well. And so you can see a heart and a circle and some squares and a high. And then going further into ultrasound simulation models, I was invited by the Ionian University in Greece, to do a collaboration on assistive reproductive technology. And so we made a simulation assisted reproductive technology model for ovum pickup. So men can easily donate, their oocytes. Females, we have to go through a whole process where they give us a lot of hormones, and then our ovaries get inflated to the sizes of melons, and then they insert an ultrasound in your vaginal canal with a huge needle, and then they start draining every follicle for an egg. I know. And yeah, I know, medicine sometimes just, makes you a little bit desensitized to things. So I apologize if I'm nonchalant about painful things or something like that. I got desensitized like 5 years ago. So, and so, they drain everything, and then they have the embryologist on site that starts looking through the fluid and making sure they find the ovum. And so here's the process of making this. We ended up using sodium alginate and calcium, and calcium chloride. And to make spherification is a process that you use in molecular gastronomy. Have you guys seen like the vegan caviar? Same. So I made a protocol so that it doesn't solidify inside and it maintains liquid, and so it's ultrasoundable, and you can aspirate it as well. So here you see kind of like the science model, the art model. You see that? Ta-da! Right? So this is much more exploratory research, and I think art has really helped me to be able to translate a lot of the medical needs to technology and for simulation and device making. And this is the artwork. So a lot of times I'll just, somebody asked me once, so how is it that you separate your art and your science? And I'm like, I don't. I try to merge them as much as I can so I can remain passionate about what I do. And so I think of things deeply, not just scientifically. I think of them artistically and philosophically. And so this is you know, a follicle simulation model that's in a bottle with my DNA. We also make a lot of suture pads, as you saw yesterday, all the demos of the students. This is a critical skill that all doctors need to learn. And from my experience, what they do as medical students is memorize and memorize and memorize. They have these like controllers. Can you guys show your controllers, please? So they have this data, I don't know what it is. It's like an application. It's called Enki. Enki? Yeah, they're flashcards. And so they're constantly trying to memorize all this information. And so when I've seen some of the residents use tools, I'm like, oh, you're a surgeon? Have you taken a sculpture class in your life? So anyway, simulation is really good. I think people need hand-eye coordination in medicine quite a bit, and sometimes we don't elevate this as much. So we made this suture pad with silicone, and we made a protocol that was also published, and to make the layers of the muscles, the layers of the fascia, the layers of the fat, and the dermis. And we also try to make the texture of the skin. And then we moved into biologicals. We use these bacteria to make bacterial cellulose. And so here you can see phase one. You know, you grow the bacteria. We're using sugar, and we're also using tryptone, which is short protein, which bacteria can digest, and so they can make these cellulose. And then you suture it, and in 1 week, essentially it heals. So here you see it. So, you know, the tensile strength and the cellulose make it so that it's, you know, much more realistic. And so then you put it back in the brine and it heals, so you can remove the sutures. The fact that it's alive is also great because it teaches students about hygiene. You know, you can get it infected. So we're working on making that into a kit. We've also done a leg fasciotomy model, and I'm just going to go through all this stuff quickly because we do a lot of stuff. We also made tactile directives for low vision and blind patients because they can't read how many drops they have to take for their medication, but they could feel them. And so we have these. And then during the pandemic, which is kind of the basis of this whole meeting, I guess, is what really spurred us to come together. We made URUS, the emergency use resuscitation system. Luckily, we were in a hospital, so we already knew about all the regulatory issues before we started doing a lot of, you know, big changes. But with that, we tried to design this. We heard the call, you know, we need more ventilators like all of you guys did. And we tried to do the Apollo 13 thing, you know? I'm like, what do we got? Open the closets, supply closets. And then I thought, okay, I'll use a blood pressure cuff inflated with the vacuum and air from each patient room has ports for vacuum and air, and then inflated and deflated at the rate. And I found a quote that fits from Theodore Roosevelt: do what you can with what you've got where you are. So this is it. And those are the schematics, which is all in GitHub. And so we made it so that it works at the top. So 800 milliliters of tidal volume at 30 breaths per minute is our best, and that's pretty close to benchmark. I think benchmark is 45 breaths per minute at 800 milliliter of tidal volume, but we got that at 450. And thankfully we had vacuum because otherwise you couldn't get it fast enough deflating naturally. So this is when we actually did the animal studies. We ventilated 3 sheep and did it successfully. The first 2 were for 30 minutes and the last one was for 2 hours, and it blew my mind. I can't believe that we built something that sustains life. And as an artist, I distilled it as well. And so this is called First Breath and this is called Last Breath, 2 artworks that kind of, you know, honor the sheep. And then I did a meditation about animal sacrifice, the cycle of life, the persistence of survival, and the anatomical, mechanical, and chemical functions of breathing in collaboration with all these beautiful people. And really, you know, as an artist doing animal testing, it was really hard for me. And so and talking to my students that have to snap the necks of mice a lot and don't know how to deal with those emotions, he said, sometimes I say a prayer when no one's around. So that made me a little bit concerned about how we are dealing with this kind of thing. And so I thought that a meditation would be a non-denominational way to do it. And lastly, I want to remind you guys the Hippocratic Oath. I swear by Apollo, physician, and Asclepius, and Hygeia, and Panacea, and all the gods and goddesses, making them my witness, that I will fulfill, according to my ability and judgment, this oath and this covenant. And I want you guys to look at this. To hold him who has taught me, if he is in need of money, to give him a share of mine. Students, the oath makes you give me money when I need it. I just want to point that out. And lastly, it also says to teach them this art if they desire to learn it without fee and covenant, to give a share of precepts and oral instruction and all the other learning, which I thought is beautiful for what we do as open source developers. So lastly, I think collaboration is the basis of knowledge. And something that I've learned around the years that I've been around is that a good collaboration is founded on mutual mutual admiration, which is a glue for trust. If you admire somebody, you're probably going to trust their opinion. And if they admire you, they'll trust yours. And so we can collaborate and fully enjoy each other's contributions. So if you have any ideas or questions, please email me. I'm super open to collaboration. I do what I can to maintain all my projects. I figured out that if I have students, I can put legs on my projects and they talk to you, so they get done. It's been an incredible system, and so I'm happy to work with outside institutions and individuals that are interested. So thank you very much.
Okay, thank you for that. So now the next talk we'll have is Lucia Tonion. Lucia is a doctor and a member of Association Gorgolab, a makerspace which is giving its contributions in developing and assembling Angelo. She has been involved in the project for 2 years, pardon me, and she is enthusiastic because she believes in the wide potential of Angelo in order to help low-income people affected by hearing loss. And so now we will hear a talk titled Angelo Amplifies Emotion.
Good day, everybody. I'm Lucia Tonion. I'm a doctor and I'm here as a member of Association Gorgolab. I send you my greetings from Italy, and also I send you the greetings of the president of Association Gorgolab, Niccolo Leali, and of all the members of the association. Thank you for the opportunity of participating in this fantastic event. I am thrilled to illustrate you a compelling example of how the open source ethos is revolutionizing healthcare from the ground up, the so-called Progetto Angelo, or Angelo Amplifies Emotions. The technical details of the device we developed in order to help people with hearing loss will be shown you by Sergio Amirales in presence. Instead, I'll illustrate you how Project Angelo is not only a device to help people with hearing loss, but it's a project about open source, inclusivity, and sustainability. In fact, it perfectly embodies the synergy between collaborative technology and compassionate, community-driven solutions, highlighting the crucial aspects of inclusivity in healthcare innovation. Here is the agenda of my presentation. I'll tell you something about hearing loss, the so-called invisible disability. This definition has been created by World Health Organization, and I'll tell you why. Then I'll illustrate you what is Project Angelo, how it was born, and I'll focus on the two main characteristics of our project. Open source, that is, we are revolutioning healthcare from the ground up, and inclusivity, that means that Angelo is easy to assemble, has a low price, and it is community-driven. And finally, I'll tell you something about the Angelo points. One of them is the association Gorgo Lab I am a member of. So let's start with the epidemiology. World Health Organization estimates that over 1.5 billion people worldwide are affected by hearing loss. So it's a very, very big number. Of them, 430 million have heavy disability. 80% are in developing countries, and the reason is that hearing loss can be caused by infections and malnutrition. And the World Health Organization estimates that by 2050, 1 person in every 4 people will be affected by hearing loss. So the perspective is a bit dramatic. Who is affected? World Health Organization says that hearing loss is an invisible disability because it's difficult to recognize it. When you see somebody who has hearing loss, you can't recognize him from the face, from something which is visible. So it is an invisible disability. This makes difficult to manage this disability. We generally think that elderly people are affected, but not only elderly people are affected. We have also workers because they sometimes have lack of protection in noisy industries. And also young people, because they listen to music or they play video games at a high volume, or they go to disco and to concerts where music is transmitted at a high volume. So it damages the ears. And also we have children with hearing loss because of congenital or hereditary diseases and infections. And this is why World Health Organization has issued a resolution in 2017, and the organization said that hearing loss is a public health issue. And why it is so important? Hearing loss causes social isolation, and social isolation provokes cognitive deficit. So you start with a hearing loss and you end with a cognitive deficit. And that is the main point. Of course, hearing loss causes difficulties in day-by-day life, driving, crossing the street, answering the phone, watching TV, going to the cinema are difficult activities to do if you have a hearing loss. And finally, it is a progressive deterioration and it is not reversible. So, World Health Organization has spread some tips and advice about how to protect your ears. And one of the pieces of information it gives is that you can use assistive technology. And here we are, because you can find assistive technology in 2 ways. You can have very expensive and technological advanced devices, and you can have OTC, that is over the counter, that is devices we have a low cost, and you can give them to people who have no money in every country. And we will talk about this aspect, OTC. World Health Organization studied OTC and published a report in which it says that over-the-counter hearing aid delivery can improve access and affordability. And so it can be useful for people with low money or in developing countries. We know that there are differences in regulation in different countries. For example, in the US, OTC regulation exists, and it has been issued since 2022. Instead, in Europe, we have no OTC regulation. Only medical devices provided with a CE mark are allowed. In Italy, we are in the same situation of European Union, so hearing aids are allowed only under medical prescription and a tailor-made technical adaptation. So let's go on with some details about Project Angelo, because we saw how the situation is and how important hearing loss is as a medical disease. Now, let's see what we did and what the Project Angelo is in details. The genesis of Project Angelo is deeply personal, rooted in the challenges of the 22 COVID-19 pandemic. It's a story full of emotions, and I'm very proud and very glad to share it with you in the next slides. The project creator, Luciano Fumagalli, faced severe communication barriers with his 104-year-old father-in-law during pandemic. His name was Angelo. Angelo was isolated in a nursing home with profound hearing loss. Distancing and masks rendered traditional communication impossible. And this frustrating experience sparked Luciano's innovative idea to create a simple device, simple technological aid to reconnect Angelo to the world. And he tried with a simple device and a simple amplifier. Mr. Angelo could hear, and this event had a profound emotional impact. This emotional impact of this first successful interaction became the driving force for sharing this invention. And so from the personal lead, Angelo evolved into a fully open source project. And here we are with the main characteristic of the project, open source and inclusivity. As for the first one, open source, the project is licensed under Creative Commons 4.0 by SA, and it received the license from OSHA IT 17. And what does it mean? It means that everybody can download schematics, circuit board design, 3D printing files, material lists in a free way from a website. If you Google Progetto Angelo open source, you can find everything and you can download it freely. So everybody can reproduce, modify, commercialize Angelo, and it facilitates viral spread, and so low and middle income countries may benefit. As for the second characteristic, inclusivity, it means that the design of the device is compact, user-friendly, colorful, as a single intuitive control. It's easy to assemble. It's a snap-fit device, so you don't need glue, neither screws, and the assembly is fast and easy. So it is accessible even to children and people with disabilities. They can assemble it. We tried with children, they are able to assemble it in 2 minutes. And so you can, this way, you can gain active participation of users, gratifying engagement, and it can be also an educational tool for STEM in schools. Moreover, Project Angelo has a bottom-up approach. Angelo points are born. What is an Angelo point? Angelo points are local hubs, such as makerspaces, libraries, schools, associations, volunteer groups. And they are very, very important because they support the dissemination and realization of Angelo devices within their community. Angelo Points can organize workshops, educational projects with students, lend Angelo devices to users, and create a local network of solidarity and competence. And so they build a collective response to vulnerability. Third of all, we have also aspect about sustainability, because Project Angelo has a low cost. We calculated more or less $30, including headphones. And it's adaptable. You can charge it using a USB or solar panel. Project Angelo received some awards, many awards in Italy. It won the first prize at the Maker Fair in Trieste in 2024 for bridging generational gaps. And it received the OSHWA certification. So to sum up, Project Angelo is inspired by open source principles, and it is driven by bottom-up initiatives. It has a deep commitment to inclusivity, and so we hope it can redefine healthcare models and empowering communities to build solutions that amplify not just sounds, but emotions and solidarity. At the end of my presentation, I am glad to show you our association, an Angelo Point, one of the 3 Angelo Points in Italy. We are a makerspace based in Italy near Milan, and you can see in the photo, in the picture, on the creator of the project, Luciano Fumagalli, is the man on the right, and then you can see many other members. And we are involved in the project in many ways. We organize an event during the World Hearing Day. We organize a conference on March. And we assemble Angelo. We assist users. And we are also collecting data from a scientific point of view. I'm personally involved in this aspect. And we are, finally, we are investigating technical performances of the device. So we have a collaboration with Politecnico of Milan. We are trying to find what the performances of the device are in the laboratory of the university. And if you are interested, you can also make your technical tests, and we are glad to share the information with you. So my presentation ends here. Thank you for attention, and see you next time.
That gets me every time. Okay, so now we'll have another virtual talk by Vittorio Lumare. So Vittorio got his master's at Politecnico di Milano, Italy, and is a robotics engineer with 12 years of experience. After his master's, he began research and development in indoor positioning robotics and many other projects around Italy and the UK, working mainly with Moli Robotics. He's now a freelance consultant in robotics and computer science, working for both local and remote clients, and started his personal open source project, Rebellia, an open source robotic hand for humans and robots, which he will now share more about today. Please welcome his virtual talk titled Rebellia, a hand for humans and robots.
I am Vittorio Lumare, a robotics engineer, and I started this project of developing a myoelectric hand because I have a friend which has a transradial amputation, and he explained me he couldn't afford advanced myoelectric hands with many degrees of freedom, sensors, because they cost too much, they are bulky. The only one, the national health system in Italy, the only myoelectric one which is given to the people by the system for free is very old and not advanced at all. It has only 1 degree of freedom. So we started to check if it was possible to make a better hand with low cost, because now the technology it's very cheaper than before. There are products ready on the market. You don't have to invent one motor. You can reuse some servo motors that already exist. So we started trying, and we ended up with one design which can it's compatible with his amputation, because depending on the length of the remaining limb, you have less or more space. So in this case, he had this space. We put in this part all the electronics and actuator we needed, and all the rest is just tendons and plastic part pulled by the tendon. So we ended up with a mechanical design, very simple. It has one tendon for closing the finger and another tendon to extend. We made a lot of research and tests to prevent lateral movement. We only want to move it forward and be rigid in all the parts except the flexible joints. And also we made in a way it's easy to replace covers. We can have covers on it. This is the new version actually. There are 2 versions. The first one has been already released, open source, and the next one will be done soon when it's finalized. We had to improve many things to make the device usable. The device has 2 sensors. I can show here, it will be shown even better afterwards, but it's just the first prototype we made. It has 2 sensors inside, and this sensor can detect the muscle movement of the flexor of and extensor of the wrist. So when you use the flexor muscle, it will flex the wrist. These people don't have the wrist. They are only the remaining muscle, but these 2 muscles often are still active, despite this kind of people often loses the control of all the other muscles. So depending on how many muscles you have a better control or a simpler control. My friend had just 2 muscles available, the closer one and the flexor one, the extensor one, sorry. So we put 2 MG sensors, electromagnetic, myographic sensors. So they are just external, put on the finger, on the skin, contact sensors. They don't need liquid or any treatment of the surface. You can just put them on the muscle always in the same place and position, and they will detect the muscle activity. We put on the closure, one on the extensor muscle, and when the closure muscle activates, the hand starts pulling with the servo motor the tendon which close the finger. As soon as you start doing the opposite, activating the opposite muscle, it starts going back until you stop doing anything. So for example, if I want to grasp an object, I have to exert some force on this muscle, the flexor muscle, and it starts closing, and at some point I stop doing anything and the hand will keep the grasp. And this is useful because the people don't want to keep exerting force while grasping an object and moving it. They want to just close, stop acting, stop moving muscles, and the hand must keep the grasp. This works very well. We tested it, and there are two thresholds. With one threshold for closing, one for opening, and this is applied to all the fingers simultaneously. If some person has more muscle available, we can add more MG sensors to control independent fingers as well, as we already can see with many advanced myoelectric hands in the commercial field. But this kind of hands cost a lot. Not many people can use them because they don't have so many muscles available. Whenever this happens, we are ready to integrate more sensor in our version, which is low cost. So instead of having a hand which costs 20,000 euro, we can have a hand which costs 5,000, and the actual cost of the components is only 200 pounds, and another 200 of man work. So it's a very cheap device. The reason why it costs a lot because the certification, the regulations in Europe is called MDR. They force the companies, it's right, I mean, it's required because they have to implement many procedures and checks and external audition in order to be able to deliver a product which is always the same, with the same characteristics, with the same safety measures. And so to have a reliable and safe medical device, the cost is a lot, because this certification cost more than 40,000 initially, euro, US dollars, pretty much the same. And then you have another expenses for the insurance and so on. So the price of a hand triplicates due to this. So people, also company want to get more earning, and so the price increase. In all this scenario, we thought we can reduce at least the engineering cost and some earnings for the company. So we have a product which it still gives promises to the company a successful business, but with reduced cost. And because we release open source, the engineering cost now is solved, already done for everybody. Everybody can get and start it. You can sell it as well. It's not non-commercial license. You can also sell it. So anybody in the world can create, print this hand assembly and then sell or give for free. And we are okay with this because the intent is to make the market so competitive that anybody can do easily the hand, and all improvement must be shared because it's a viral license. So you want to do it, you have to release it. You want to improve it and make money with it, you have to release it. You do something which improves the hand so much, everybody will get this because you must release it. And then so we will end up having very advanced robotics hand in all the world, and everybody can do, many companies will be able to do this, and the price will go down very much. So this is the intent of the project. The device works. We tested many ways. We also made some effort for conditioning the signal, because there is a much noise to detect the muscle activity, and usually there are many steps. You do convolution, you do the envelope. We ended up with an FFT filtering which isolates the band that we need, and then with some thresholding we could obtain a signal and a reliable control. So when my friend, which tested the hand, this was made for him, unfortunately he cannot use it anymore because he made some gym and his arm grew a bit, doesn't fit anymore. But he can control very well, and when only he decides to close the finger, they close, and if decide to open, they open. If he doesn't want to move them, they don't move. So we tested many times. It's reliable. There are 2 batteries inside in this panel, and now there are screws to remove. We're gonna make the next version more easy, so you don't have to use screw to remove the panel and replace the batteries. So we made a new model. It's no release yet. Will be. It has all these advanced features. You can remove the plastic very easily and put them back. And also this part, if you want to maintain the tendons, do some change, it's very easy. And also you can change the color, and you can change the color, anything. And so this is very versatile project, and after the signal conditioning and all this improvement, we tested it, and I have to say we were surprised by the result. And so we started thinking we can start distribute in some way, but the regulation makes this impossible, because you have to do a very expensive process. And then we started to concentrate on the robotic version without the socket, only for robots, to get a product at low price without all this regulation and costs, with the intent of improving it and obtaining a successful business which can produce earnings and give us the possibility to be on the market, to be positive in business. And so this should help to obtain a reliable product in a few years with earnings which permit us to also start the other project, the prosthetic version, which now it's impossible, at least for me and my small team. So the intent is to have 2 products, the robotic products and the prosthetic one, both open source, both you can do, improve, copy, sell, whatever you want. We will do the same. Everybody, we hope, will do the same, and so we have many versions which will probably converge into a very advanced one, which anybody can still get and produce and sell. So this is a solution which is effective. My friend used it. It could grasp many objects. Could open a bottle of water. Perfect. It could open a door, pressing buttons, grasping objects very reliably. But in order to get this, we had to do several improvements. And the most important one we discovered was the grip. So having a hand which can close reliably and you can control it reliably, and you can decide I want to close it more, a bit less. It's good. It adapts to the object because it has tendons, not gears, so it basically closes until it touches all the part of the object. It's closing over it. But there was a big problem. The object tends to slip. There was no grip. So our skin has a very good grip. Many robotic hands are made of silicone, which is the best material for the grip. And so we had some pads on the hand, initially of rubber in the first prototype. And the current one, you have to glue the rubber pieces to the palm, to the fingertips, and you have a very good grip over the objects. This helped us to grasp an object which couldn't be possible. Even object large like this, like 15 centimeter diameter. So it's a big hand. I made it over my friend's hands and mine, which are basically the same size. So it has a size. We plan to make it of different size, obviously. And in the new version, we will use silicone pads, which cannot be printed at the moment, or you can with some special printers. It's not easy to have this kind of equipment. So we made in a way that anybody can do. And we print the finger with the TPU, flexible. It has flexible joints with also PLA inside materials to make the print more solid and to prevent some distortion of the finger. So it can move only in one way that we want. And then the final material is cast by manual injection molding. So we prepare a cast and then put exactly, it matches the face of the front of the finger we wanna produce, and then inject with the syringe the liquid silicone, and then it solidify after some hour. And this is the most advanced kind of piece we made for this hand, and it will be delivered in the new version. The version number 2 is not yet delivered. We have to improve it. But the expectations are good because our test prove it works very well, and we will put even more features, and all will be released by open source. So we will have we can anticipate we will have a hand which can auto-calibrate, which can limit if the temperature raises too much, preventing risk of burning, risk of fire, risk of damaging the motors, and also limiting the maximum tension for the tendons, preventing the breakage, the uncalibration. Even though the hand will calibrate anyway automatically every time you start it, sometimes it may need some manutention, some maintenance. So you have to open the back panel and register some tendon after some months of usage. And to make this even easier, we made all snap fit, so there are no screws to remove. You just remove by pressing, the plastic pops up, and you can maintain the hand. In the rarely times is needed, because again, the auto calibration and the force limitation will make sure there will be no need so much of doing this. It will happen very rarely. And all this system we made, this control, also provide another good functionality, that you can grasp objects without knowing the shape, and the hand adapts to the object automatically, stopping the force exerted by each motor when it surpasses the threshold that we want. So if at some point I want to pick a very fragile object like an egg, I just have to set the limit of the force lower to the minimum level, and the hand will start closing around the object. When it feels a bit of resistance, it will stop suddenly. And I can choose different levels of closure strength, up to the maximum limit over which one it will create problems for the hand integrity. So we cannot go over the threshold, but the threshold is very high. So the hand is strong, it will be durable, auto-calibrated, and I hope this will be appreciated, and many people can contribute to this project to make hands even more accessible in all the world. Thank you for watching. Bye.
Perfect. Okay. So now we're going to have Jean Rentoul, who is the founder of Mind's Eye, working on novel ways to interface with the brain and body.
Hello, everyone.
Prior to this, she garnered a PhD in neurotechnology with a background in biosensor wearables and medical devices. She'll be giving her talk titled Spectra, Portable and Open Medical Imaging, How Far Towards Diagnostics Can It Go? She'll say the title better. All right, with that, I'll give it to you.
Great. Hi, everybody. Yeah, so I'm going to talk about a project that I started some time ago. This is some older slide. Is there a newer version? But this would be fine otherwise. So basically, So basically, imagine a world where medical imaging was easily accessible to everybody. Basically, 2/3 of the world doesn't have access to medical imaging. It's a lot of people. It would also be neat if we could, even in a first world country, use medical imaging preventatively instead of when we think something has gone wrong already. We've got MRI, which is very expensive, helium quenching chamber. It's wonderful that they've got the MRI for all, but we've also got a CT scanner, which is based on X-rays, sending them through different angles, which measures something slightly different to what an MRI measures. Ultrasound was still expensive, about 80K for a medical grade system, and of course EEG, which for a diagnostic level clinical grade system is also K plus. So why make medical imaging in general more accessible? Well, if we can look at computing, where it started being the size of a room, and then in came the desktop computer, that really changed how people interacted. Everybody could now interact with computers. And I think this is what actually brought about this computing revolution, is that we were able to shrink the technology and make it available, democratize it. Then we shrank it some more and we all have one in our pockets in the form of a smartphone. So if we take a step back and imagine we could do the same thing with medical imaging, an MRI, yes, it takes up more than a room because it also has a helium quenching chamber, it has dedicated personnel. It's really big. But what if there was something small and portable that let everybody do medical imaging? I mean, we've already got TV shows like Star Trek when the tricorder, the sort of good for everything health diagnostic device. But so far, that's just a dream. So basically, what would happen if there was a safe form of medical imaging that people could hack with and improve? So I came to this actually from a failed startup. I'll just put that out there. So me and 2 other co-founders, we got into this accelerator called HACS. We made a bioimpedance spectroscopy device that measures how full your bladder is, aimed at people that have neurogenic bladder disorder, which is people who have paralysis or have had surgery so that the nerves in their bladder can no longer tell them when they need to go to the bathroom. It was meant to be a wellness device so that it would have an accelerated path to market. But something went wrong. Although it worked, we started to go through this FDA process, and positioning it as a wellness device was not okay. It was perfectly safe to use. It's within the IEC 601-1 guidelines for safe use in humans. It's external. It's not even an implantable. However, because it's to be used on people who have a medical condition, people who can't fill their bladder, that makes it a medical device. So this put our small startup in a very different position. So we now started conversations with the FDA, and they wanted, first of all, nobody had done this before, so it was a de novo device, which means it hasn't been put into one of the class 1, 2, 3, or 4 type medical devices yet. And then next, they wanted long-term trials. And we thought, wow, long-term trials, like 5 to 10 years. It was really nice that Accelerator gave us 100K that all 3 of us could share and build a device with, but that's just, not really going to cover it. So anyway, so I went off and I got another job, and I kept hacking on this bioimpedance spectroscopy device on the side. And that's how Spectra was born. So Spectra is an open source electrical impedance tomography device. Electrical impedance tomography is very small. All the parts are very low cost, so it can be quite easily mass produced. And what it does is it can image through a cross-section of material. The material has to be conductive, being the only quality that you need. And obviously our bodies are 80% water, that makes us conductive. So here is an example where we're reconstructing an image in a tank filled with water. So you can see a cup moving around and the image is able to be reconstructed. Similarly, here's 2 cups there. And you can see it can reconstruct an image of those 2 cups inside this tank. So the way that it works is that you send a sine wave, an AC signal, through the medium, and based on the qualities of the medium, whether there's fat, muscle, a tumor, in this case, a cucumber or a carrot, they have different material qualities, and the current will go a slightly different path based on the relative impedances. So if you do that and you send it through at different angles, you can reconstruct an image. So the way that this works is that you send out a current and you measure it on the other side, and it will have lost a bit of energy, it would have attenuated a bit. Then you send through another current and it will have lost a little bit of energy if it goes through at a different angle, but it will be a bit different at each of the different angles that you send it through at. And you do this for all these different angles, kind of in a circle, and you use something called the radon transform, which is what they use in CT scanners. So this is the same technology that is used in CT scanners, which is an interesting thing because you could then learn about that technology, you see. Whereas it's probably very hard to just play with a CT scanner in your spare time right now. Also, they're ionizing radiation. Wouldn't recommend it, not good for you. So you use this and you can reconstruct an image, and this is how you do it with the current. So you can see you inject the current, and then you measure it from all of the other electrodes, and then you move over the current one and you measure it from all of the electrodes, and using that you can reconstruct an image. So here's an example of spectra and lung imaging. So this is one of the classic use cases of electrical impedance tomography, which has been around for quite a while, by the way. So lung perfusion imaging, basically looking at air which is non-conductive, filling in your lungs, and how your lungs expand and contract. Now, the resolution of this image isn't very high, you might notice. But that's okay. If you remember in 1977, in the first MRI scan, it looked like this, pretty low resolution. And then an ERT scan, pretty low resolution, but you can still kind of see that there's some lungs there. And we've come a long way with MRI. This is a scan actually of my brain, and it's so much better than what it used to be. So the question is, can we do the same with EIT? It would take some effort, but because it's so small and mass producible, surely that would be worthwhile. The other thing that it can do is impedance spectroscopy. So this is a massively underutilized technique, in my opinion. So basically you send through frequencies, a range of different frequencies. And what you can see here on this part here is that if I put an apple and a sweet potato in a bath of water, and I measured their spectrum, and you can see that the apple and the sweet potato have a different spectrum to one another. But what's even more interesting, that spectrum remains the same over subsequent days. So it's kind of like, yes, the apple and the sweet potato are constantly different in the same way. So this is important. If we imagined that we replaced that apple and a sweet potato with cancerous tissue, or something else that we wanted to find, a liver abnormality, kidney stones, something that we want to search, where we want to measure a material difference. And we can also, this is just 8-electrode EIT, bit lesser. I did a basic machine learning algorithm over this. I think it was k-means clustering. And based on the spectrum, it can classify the apple, the sweet potato, and the apple and the sweet potato together correctly, which I think is kind of interesting. If you could get this to a bit of a high resolution, you've got this pretty accurate material identifier. So this project actually started quite a while ago. It actually started around 2017. I did a presentation at a hacker conference in Germany of the first 8 electrode design. I beefed it up to a 32 electrode design and showed it at DEF CON and Biohacking Village. Then there was a Hackaday Super Conference, IEEE Brain. I did a crowdfunding campaign for it and delivered it to over 100 backers. So it succeeded. And then it won this Accessible Science Tools Award from the Gordon and Betty Moore Foundation, which was very helpful. So it came quite a way. However, I wasn't sure that it was really, that this was sort of something that I was thinking, this is really awesome, but I'm not really sure where it's going here. And I ended up deciding to start a PhD, which I've just finished. So I disappeared off into PhD land. And now I've reappeared, hi. But I kept selling it. I wasn't advertising it. While the first few years of the PhD before a part supply shortage occurred during the COVID pandemic. But I think it's interesting to see what effect this device has had and who's using it. A GI doctor in New Zealand who's monitoring gastric emptying, a prosthetics lab wanting better gestural control so you can get a cross-section of your wrist to see muscle movement, a dentist wanting to replace x-ray machines for cavity detection. That's a great idea. There's a startup that got one. They want to do embryo analysis for bovine in vitro embryo production as a proxy for later human in vitro embryo analysis, but bovine in vitro embryo production is a massive industry, which I wasn't aware of until I met them. Sleep apnea analysis for the throat. So in this case, you stick the electrodes on your throat. Cerebrospinal fluid for measuring intracranial pressure post-neurosurgery. A body and fat analysis tool. This is like an oldie but a goodie, like the bioimpedance scales that people use to measure fat mass versus muscle mass. Deep vein thrombosis monitoring. Fertility prediction, another startup, KEG. Lung perfusion monitoring for pulmonary embolism. So there's a few different labs that are looking at this application for EIT. That was University College London. And then there was another startup, Pathfinder Medical, for advanced fistula creation for dialysis. So this is there's a lot, many more, hundreds more as well. So I think this is kind of interesting that it can be used for so many different things. And I felt good about it momentarily. Encouraging innovation and the acceleration of health technologies. And then I put a question mark. Because we're not actually impacting patients. There's no patients. So there's no diagnostics. There's no actual diagnosis. This isn't really having an impact. I mean, it is having an impact. Our labs are buying it. That's good. It's better. It's very good. It's wonderful. It's gone through no formal safety qualifications. Those are expensive. And it comes with a little phantom for you to use and experiment with. And if you want to put it on your body, you're doing that at your own risk. It has to be like that. Otherwise, it would need to have gone through a lot more certification to sell it. So there's limited funding to continue or support the acceleration of development of a tool like this. And that means that we don't benefit from the end use case of helping patients, nor do patients benefit. And nor do VCs really love funding medical imaging innovation, and I can explain why that is. Basically, pharmaceuticals has a similar path to market, yet it has much bigger returns. So medical devices in general aren't popular to fund, just as a full stop item. And this is going to flow back all the way through into healthware considerations. And I think that's just interesting to think about it, because it's actually just a general problem in innovation in healthware, medical devices in general. And this is a travesty of human health This is like I think we could talk about the Hippocratic Oath and all the missed opportunities of preserving people's health that we're missing out on here. So let's have a look at what the venture model for medical devices is and how you actually get a medical device to patients. This is where it's meant to do the good. So basically, there's a limited appetite for technical risk, and you need an IP moat to get venture capital. So you need to narrow down to a single diagnostic application right at the beginning. I've already gone far wrong. Okay, far wrong. Look at this, so far. Okay, so single diagnostic application, narrow as possible. And that's sort of sad because it could be used for so many other things. And then you should do clinical trials on that single diagnostic clinical application. That could take quite a while, 5 years. So you don't really innovate. You don't have a time to refine. You've just picked something that can be fast relatively to market, and you have to shut down the technical development and innovation so that you can get through those clinical trials. So that means that we're not really experimenting at any stage in medical devices. We're not exploring how to make them better. There's something wrong there. So insurance reimbursements, that can take about as long as clinical trials. So now you have the regulatory and IP moat that you need. And maybe in 10 years, if you're lucky, you can generate some returns for the people who have invested in this company. So this is the model that we're looking at. This is how you actually get to patients. If you're not doing this, you can't diagnose anything. And you can't really take it to patients. So that's a problem. And I thought to just contrast it, to consider the development pathway of MRI. I love MRI. MRI is really cool. 1952, the Nobel Prize, but basically material science applications. They did a whole bunch of different things, enabling spatial specificity, the conversion into images. You can see all of this basic innovation, basic physics work that's occurred. And this is very important because it wasn't used medically initially. And then it didn't have anything to do with medical care. In 1983, Siemens installed the first MRI at Hanover Medical School. And from that point forward, it went through a series of clinical trials and rolled out to more and more hospitals and continued being technically refined. But this is over a period of 60 years. That's quite a while. And clearly, it's had quite a long time where it's been in this experimental development phase. So now I'm going to scoot back to open source healthware and sustainability for long-term impact. So this EIT device, it's unable to have impact on patients because of these regulatory hurdles. There's all these other certifications that it would also need, like to be produced in ISO 13485 compliant factory and ISO 60601-1, and there's all sorts of other things as well. So longevity of projects. Does the development end? So when people get these grants to develop open source, another problem is that to get a medical device all the way through to helping people, I think it's about a 10-year time frame roughly. Does the development end at the end of a grant? Or how do we sustain these innovations that you guys are coming up with and keep them going? There's minimal funding support after that. And you need funding support for usability, maintenance, UX, tutorial development, training and support, technology iteration, manufacturing and distribution. So these are all things past the novelty stage. So this is past the point where you've written an article, which is where most of the scientific energy goes into, which is wonderful. And there is definitely a great place for that. And that's very important. But it also you need to do these other things to get it out there. Upsides, interesting and fun collaborations. and you get early feedback, which is wonderful. And you can get it across a broad range of applications instead of just one clinical indication. That means that you can be fast to market, bypass the longer regulatory hurdles, as long as you've limited your risk appropriately. So you have to find a way to not be going past any of the limits that would otherwise be set. And obviously it helps other people in medical devices to help and improve access. So I think there is value in this. And the value is actually in encouraging other people to innovate in medical devices, which is otherwise very hard to innovate in because of this kind of very narrow timeline which we're subject to. And just to bring up the people on the other side of the equation, which is wearables, Apple has a lot of money, yet still it's very limited in what it's actually diagnosing. It has to say it's inconclusive a lot of the time. So a problem with diagnostics is if you're correct 98% of the time, that's not enough, because you're legally liable for that 2% that you're wrong. So there's a very fine line to negotiate around. There was a company called Whoop that did a blood pressure monitoring wristwatch, which looked really cool. And it was marketing its blood pressure monitoring as a kind of wellness metric, which also sounds interesting to track and potentially very useful for many people. But that too, you're not really allowed to expose to people, which is, in my opinion, a bit sad, because this is information about our bodies, and this is just how our bodies are, and we should be able to interpret that information how we wish. So there's some problems there. So what are my future plans? So basically a revision. I'd love to do a revision of the EIT kit, basically taking the user feedback on board that I've got by having different people use it. And I'd also love to do a new prototype based on my PhD work on this other form of imaging called acousto-electric imaging. So thank you, everybody. I would like to say that there's a GitHub repository. You can look at tutorials, openeit.github.io, contributors, discussion forums on there. Got a mailing list that you can sign up to with over 1,000 subscribers, active Discord community chat, and I'd like to say thanks to everybody who's been involved. Yep, thank you.
All right. So now we have two speakers going to give a virtual talk, and those next speakers are Chris Rexroth and Addie Cobb. So Chris is a biomedical engineer who looks forward to a world where corporate interests do not interfere with medical advancements. He currently works with an implantable device that is being studied under clinical trials in people with spinal cord injury. With Cosmic, he is preparing the documentation of that device so that other researchers developing human therapies can use it themselves. Addie is the head of the OSPO for Vero Life Sciences, an organization founded to develop technologies that prevent the transmission of diseases. She's an open source advocate and a community management expert with over 20 years of expertise and experience leading transformative initiatives across the globe. She has worked with companies such as IOHK, Tetra Technologies, Elanco, and Analog Devices. Their talk is entitled Opportunities for Open Healthware Community Mobilization Informed by Experiences of High-Risk Classification Devices.
Hello, everyone. My name is Chris Rexroth with Cosmic.
And I am Addie Cobb with Varo Life Sciences.
We are collabing today to give a presentation on steps forward for community mobilization in the open healthcare community. So our presentation is coming in the wake of the open healthcare workshops where we've seen some opportunities for our community to come together and build some shared resources. So in our presentation, we'll be introducing our individual projects, and then some problems and lessons learned in the regulatory space and other problem spaces. Then we'll be talking through what next steps exist and what available resources could contribute to those. I am personally a member of OSHWA and representing Cosmic, the open source implantable device initiative. Cosmic's main goal is to increase access to human-ready therapies. We work with researchers in the field of neuromodulation, which is using electricity inside of the body to either restore physical function or diminish unwanted symptoms. So what that can look like is a cochlear implant, which helps somebody hear again, or reducing pain signals to help somebody live a more comfortable life. We believe that we can help these therapies get to market sooner by making it easier to develop the technology. So a researcher working in this space who wants to develop implantable technology is going to run into decades of development and millions of dollars of costs to develop their own design. If they want to use an existing device, say by Medtronic or Boston Scientific, that device is going to have very fixed specifications for its original use, and is going to be hard to customize towards their new research application. There's also a very expansive regulatory and quality expertise that is needed to get a device not just to the research stage, but to market. And researchers are running into intellectual property complications. They want to know that the system they're using is going to be available to them for as long as. So instead of using one of these systems in some limited way, or designing a new one, why recreate the wheel? There's already the Cosmic system, our implantable device, which is already being used in 10 humans for a clinical study. It has a modular design, so there are different aspects of the technology that can stimulate and record nerves. And by putting out the open source design, we've now made it customizable. So the major value that comes from making this technology open source is an alternative for access. A researcher or startup using this device has the freedom to commercialize whatever findings they make with it or any alterations they make to the device. They have open access to the design and documentations. We're adding in resources that they need to be able to get this through the FDA. And most importantly, it is already being used in humans and already been through the FDA through an investigational device exemption, or an IDE. So I'll be using that today. Thank you. Now on to Addie.
So I represent Varro Life Sciences, and we are a proud member of OSHWA, the Open Source Hardware Association. Our organization is really passionate about preventing the transmission of infectious diseases, airborne pathogens, and we believe that in order to prevent the transmission of these pathogens, you have to be able to detect first what's in your environment. And so it starts with diagnostics and understanding what you're exposed to. I know we all had the experience of living through COVID, which was a really big awakening for individuals across the globe, realizing our exposure to our environment and the air around us. Today, we're sitting in an auditorium, we're sitting in our rooms, and we are not aware of and don't have the knowledge of what's around us. As you can see from this slide, there is a rapid escalation in pandemics and epidemics across the globe. And this is certainly not a comprehensive list, but it gives a perspective about what we are currently exposed to and experiencing as a society. And it doesn't just stop with pandemics and epidemics. It also goes on to allergens and to molds and to funguses. And so there's a lot of different airborne pathogens. And so when we think about diagnostics and the detection of airborne pathogens, we need to look at kind of what the current scenario is. And so we can all think back to the periods of COVID when we got to experience a nasal swab, which was exceedingly painful and very invasive. Wasn't a comfortable test. And then, of course, you have a slow readout time. So right now, current testing shows a minimum of 15 minutes for you to understand what the result is. And that 15 minutes could be the difference between an individual being exposed and many, many, many individuals being exposed. Another component of current diagnostic landscape is that it's expensive. Depending upon the type of pathogen you're testing for and the diagnostic equipment that's available to you, some of the costs can be upwards of hundreds of dollars. And lastly, the adaptability to new pathogens. There's limited options for testing of viruses, bacteria, fungi, allergens, and molds. We just don't know. And when we have a new emerging pathogen, we just don't know. We don't have the capacity to rapidly develop tests that support understanding and detecting what's in our environment, specifically our indoor air quality environment, right? Providing that quality of air that we're all breathing in shared spaces. Varo's platform technology and current product suite houses 3 products. We have a biosensor that is modular and customizable to different pathogens. So you can test and screen for different multiple, either singular or multiple pathogens with our biosensor, our MIE. So the next thing is our breath-based diagnostic, which allows you with a simple exhale in 60 seconds to know and have a diagnostic result for what you've been exposed to. This is a vast improvement on the current 15-minute wait time for a readout. And then lastly, we have the air biodetector, which is a continuously monitoring indoor air environment tool. So it will give people in shared spaces the capacity to know what is in their breathing space, as well as with that knowledge, you get to decide and make proactive decisions for your safety and the safety of the people around you. And in fact, making preventative measures more possible for everyone to live a healthier life. Our technologies and our commitment to open source are so that individuals across the globe can be more proactive and be more informed about what we all breathe in every day. And so we can take healthy steps to know our surroundings, to know what we can do, and to take the next step to take care of our safety as well as those around us. And we are open sourcing this so that people can innovate on this and develop other tools that help them understand the air supply that they have been exposed to, and what that means for their health and their family's health and their community's health. Chris and I had the opportunity to attend multiple open healthware workshops recently, and in our dialogue about this opportunity and what that means to our individual organizations, as well as us together as we look at developing that ecosystem, we wanted to bring forward a couple of pieces of information. So I'll turn it over to you, Chris, to talk through the next stage.
So what does it mean to be a project in this open healthware space? That's certainly something we've been trying to figure out with Cosmic. So what is the full source to a medical device, and how can we make it easier for someone to adopt our design? So that looks like including into the full source beyond just the circuit board, the software, firmware, to include manufacturing information. How is this going to be built? Because that is important to the FDA. What does the biocompatibility data look like? Is it going to be safe interacting with tissue? How is it being sterilized? As well as how can we make it easier for researchers to adopt this and get it through the FDA so that they can use it in humans as well? So our goal, as you can kind of pick out, is to help other people get their own investigational device exemption approval, their own IDE approval, based on our existing technology. We at Cosmic have already filed certain questions to the FDA about an open source medical device. Here are some of the takeaways from their responses, which you can also see on our website. So there's this concept called right of reference, which allows a new submitter to the FDA to reference an existing piece of data or design that the FDA holds from another submission. So we, as the holder of the design of the Cosmic system, want everyone to be able to reference our design for their submissions. We submitted this idea of a blanket right of reference, which would allow anyone to reference our data freely. And the FDA decided that there needs to be a bit more supervision and a more personal stake in that transaction from an organization. So that is one opportunity for our community to come together and create some type of standard way of action in that process. Another response from the FDA let us know that a new user of the device should be able to inform their risk analysis with what has gone wrong with the device in the past. This is called a device-related adverse event. And there are existing databases for commercial devices that hold this type of information. We asked the FDA if we could use that database, and they said no. One success, though, that we have had is our first new IDE being approved to use the Cosmic system for something new. So currently it is being used in people with spinal cord injury for hand function, and now there will be a study for restoring walking in people with spinal cord injury. So these responses highlight some opportunities that our community could work together on. First, I think there's an opportunity to create guidelines for sharing extra stores. So the workshops have defined quite a bit of what is in that full source. I would also propose that pre-submissions and openly sharing them is almost an obligation for us in the open healthware community, because that allows us to, in one way, hold the FDA accountable with their responses, but also know the trends in the FDA responses that are coming back to our open healthware projects. There's an opportunity for making it more efficient process for right of reference and master file. There's opportunity for us to create a shared database that exists below the commercial level of device-related adverse events. And these are things that could really help adoption of open source medical devices at the FDA investigational device level. Another thing I'd like to mention is that at the FDA, they want to make sure first and foremost that they are getting quality submissions that waste their time. So in the open healthware community, we have a mandate to make sure we are doing our best to use all of the full source to put in our most quality submission. So just because there is a precedent like the Cosmic system, a new user of this system should not just copy and paste information, but should make a well-informed submission, and that can help create legitimacy around our open projects.
So another thing that we talked about was the problem space. So specifically open source adoption in the healthcare industry, which is, as we all know, a very proprietary industry. There's been limited open source adoption. And so in looking at that, we talked through how do you support an ecosystem and what considerations or things need to be addressed in order to make that ecosystem flourish. One of the highlighted opportunities is building understanding around the open source business model. So many practitioners and business leaders need to have an understanding about what will support their business, how open source supports their business, how to form a business model around the open source principles. Another item that we talked about was compliance with the open source definition. So a lot of medical research is a long-term investment, right? So within the United States, for example, some of that research starts in academia and is federally funded. Well, if you receive federal funds, you fall under the Bayh-Dole Act, and certain components within the Bayh-Dole Act are prohibitive of actually meeting the open source definition. And so as an industry and as practitioners in the healthcare field who are trying to drive open source adoption, it's really important that we find a way to legitimize our practice in being open. Because while we may not meet an open source standard, we are driving towards openness, which is the ultimate goal. And really kind of finding a way to illuminate and highlight that working and help others come to that same appreciation. Another piece that we discussed was as an industry, the healthcare world is not very for failures, which is not really surprising because nobody really wants to see healthcare failures. And so trying to form spaces that are dedicated for research use only, or RUO, so that people can find ways to make adaptations or innovate on technology that exists currently for global applications and for individuals who may not have had the capacity or the ability to look at devices or start something from a fresh place, right? If you have an open space with RUO devices, you have the capacity to innovate and build adaptations that might serve a new population or a populace that is currently underserved, democratizing the opportunity for and access to healthcare more broadly. Looking at some of the struggles that the healthcare industry has, we found and talked about a couple of steps that would be helpful. So one, understanding the current regulatory and policy landscape for open source adoption is going to be really critical, and building a knowledge base around best practices for future adopters, right? Because the regulatory and policy demand is very extensive for people who operate in this industry. The next thing that we think would be helpful is advocacy for some reform around policy and regulations, simply because there needs to be some alignment as well as understanding around what the open source practitioners in the medical field do and how it brings value to the field as a whole. Lastly, and I touched on it just a minute ago, we feel that driving open source understanding and promoting the virtues of open source is going to be really key for medical device stakeholders broadly. As a predominantly proprietary industry, there's not a lot of understanding about what the values and practices are from an open source capacity. And so that necessitates that kind of support. I am going to turn it over to Chris to talk about some resources that we have collected.
So where do we look towards to understand the current state of OS adoption? And where do we look towards to move forward, to move towards advocacy and policy change? So we started a list, Addie and I, of different community connections and guides that are out there in the open source world. Addie's talked about InnerSource as being a great way to introduce non-open projects towards the concepts of open source development. There are obviously everyone in the room today for the Open Healthware community that can be an active participant in this, but this is really about starting the conversation on how these different groups can work together to create new resources relevant to Open Healthware. So I would say thank you. We hope that this spurs conversations to push towards the next step of the Open Healthware community. For Cosmic, you can connect with us through the QR code in the link tree or my email, and I look forward to talking to you all.
And for Varo, please use our QR code to learn more about us, and you can reach out to me either in person here or via my email. Thanks.
Thank you.
All right. So now, before our break, we're going to have one more talk, and that talk is Sue Tappan. So Sue is a member of the Spark Data and Resource Center, which builds and maintains the Spark portal. She's excited about fair data and open science, and currently works on creating a software tool for curating scientific knowledge about peripheral nerve connectivity. The talk is entitled Spark, Bridging the Body and the Brain Using Fair Principles for Data, Models, and Devices. Let's give Sue a hand.
Hi, everybody. All right. Just 1 second. Okay. Okay, so it's a great pleasure to be here. I'm a fish out of water here. I don't do anything with hardware. I do find it very exciting, and I've enjoyed my entire time here, just soaking up all of the diversity and just enthusiasm for all the different ways that you can make a difference as yourself and with a community. And so I'd like to tell you a little bit about our project, and I'm actually hoping to solicit some assistance from your experience, your knowledge on how building community becomes such a success like it is here. So as in the introduction, Spark is a peripheral nervous system systems physiology data ecosystem. So we're interested in simulations, maps, knowledge, and data. And to give you a little bit of insight into how we got started, we are funded by the NIH Common Fund Program, and it stands for Stimulating Peripheral Activity to Relieve Conditions. And it's to promote a more effective and targeted neuromodulation therapies by providing scientific and technological foundations for future biomedical devices and protocols. So there were 2 talks today, one just by Chris and yesterday with Alex. Those 2 projects that they presented are also funded by the Spark program. And the group that I work with is established to build a place for all of not just the devices, but the data that comes from those devices, data that is supported to help inform how those devices should work, and tools in order to make those all of those things discoverable and interoperable and reusable. And so it got started in 2015. And in 2023, we became an open repository. So we are accepting contributions from the research community that relate to bridging the body and the brain. So everything that you guys have spoken about today, all these different tools and applications that you're creating, actually help build that bridge from the periphery to the brain, solving particular problems. And so I'm only one part of a giant consortia. This is a picture of who we are as the Data and Resource Center. We are distributed globally. We have our simulation core is based out of Zurich. Our biophysical and anatomical model core is based out of Auckland, New Zealand. The knowledge core, which is what I'm a part of, is based out of San Diego. And then the data management applications and development is based out of Philly. And so we're all supported by the NIH Spark program, and we exist to support the research teams that are also funded by NIH under the Spark program, like Chris, like Alex, and these other research aspects that I'm going to give you a little bit of information about. So our goal is to establish data reuse as a consistent part of data dissemination. We really want to allow people to see that the data is the primary outcome of their experiment. It has great value, but it gets distilled and hidden away in the interpretation that is published as a publication. So we want to raise the level of how important data is to not just the interpretations that they make and present and build their body of work with, but also it's a great resource for the rest of the community. Helps you build collaboration researchers who have a different hypothesis that they might want to test that's in relationship to an area that you're interested. Maybe your data actually encompasses a little bit beyond your narrow focus for the question that you wanted to answer, but it fully covers someone else's question. This helps lower that barrier for the experimental cost, because now if the data is available, it can be reused without having to regenerate it. But in order to do that, you have to make sure that the data is understandable and accessible. And so that's what the DRC is established to try to help address. And so we fully believe in the power of convergence. We think that molecular medicine, neuroscience, engineering, computational science, and all you hardware makers all get together to create these devices to diagnose and treat diseases. It takes this entire village to do so, and we should all be best friends. And so from the Spark perspective, Spark is focused on the autonomic nervous system. So that's the involuntary control. That's the things that keeps your organs working and all of the involuntary actions that your body performs without you making too much of a impact on. And so the data that is coming in now to the Spark portal represent 3 specific areas that is incredibly exciting. The open source implantable systems, Cosmic and CARS, really represent just an incredible opportunity to have open source hardware to lower that barrier for everybody else to really make real change. And it's such a hard problem. I'm so impressed. But in order to help inform that, we also need to know a lot more about the vagus nerve. So the vagus nerve is the largest nerve in your body, and it does lots of things. It involves all of this autonomic control, but it also has actions for somatic and muscular control as well. So in order to better build devices and intervention therapies that involve the vagus nerve, which is the best target right now for bioelectronic medicine, or the most common target, we need to know a lot more about it. We need to know how variable it is between person to person. And so the largest data set of human vagal anatomy is being conducted right now. And the insights that are coming from it are so critical for individual device design. So for cuff design, for example, how these fascicles inside the nerve twist like spaghetti. And that has a big impact on how you design your cuff to sit alongside that nerve in order to stimulate what you want and not what you want. So you want to make sure you put that nerve or the stimulation device in the right location so that you get on-target effects with minimal off-target effects. The way that we're also informing that is with first-in-world data sets of multi-system effects of vagus nerve stimulation. Vagus nerve stimulation is used in for a lot of different applications, including epilepsy, drug-resistant depression, gastrointestinal applications as well, like Crohn's disease. And you can imagine that if you have a device that stimulates the nerve, you also want to know not just the good things that happen. So yes, you are limiting the gut motility so that your Crohn's disease is better controlled, but you also are impacting other aspects of your body. And so understanding how all those things play together is what this whole impact is about. In addition to that, though, we're now supporting and bringing together data about pain. So the Rejoin and Precision projects are focused on pain due to joint disorders, so arthritis, osteoarthritis, rheumatoid arthritis. You may know about the most recent FDA approval for the RA device. It was just approved earlier this week. That was really cool. And then Precision is looking at the individual differences between people on how their genes in the are changed in response to pain in the spinal cord. So lower back pain, for example. What makes them different? Why is it different? How can we understand that? And so bringing all of that diverse data together is what we're interested in doing. And we're hoping that having all that data, all of these opportunities of all these different research disciplines together will also help inform our desire to create in silico models like digital twins, which is what the VITAL project is about. That's an EU project that's looking to create better representations of ourselves based on what we can anticipate from the various models that we have. So we want to make meaningful scientific data sharing. And in order to do that, we need to integrate this approach. And that requires that the data sets be well documented and understandable, not just by the people who create them, but anybody who might be interested in understanding a little bit more about it. We work to try to address that. And the way that we do that is by working to create a place where all that data can coexist in a way that it's been harmonized, so you don't have to understand all the intricacies in order to get into an area of knowledge, and then also provide tools so that you can do something else with it. So in order to do all of that, we adhere to the FAIR principles: findable, accessible, interoperable, and reusable. And by doing that, we can build this repository that is multi-species, multi-domain, multi-resolution, multi-scale, everything from electron microscopy to systems physiology, to CT scans, and to devices. And by having a similar and unified set of principles to arrange and align that, it makes it available for others to operate on. So how we do that, the principles that we have employed in order to help make that happen, is that we consider every contribution to the portal as a data set. It's a computational data set, it's an anatomical data set, it's an experimental data set. Each data set has structured metadata, a predictable folder structure, so that as you are accessing this data, whether it's by visual exploration on the website itself, or by API access, you know how to retrieve what you want to retrieve. Additionally, we adhere to minimum information standards. So that ensures that each data set, regardless of what it is, has a minimum amount of information that allows you to understand what's there. We also adhere to common data elements and a controlled vocabulary. This is the part of the project that I play that's my area of where I work on this project. And if you know anything about the human body, you know that there's lots of names that are used for the same thing. And so that is an extreme problem when you want to harmonize and use data, right? You're going to call this the head. I might call it the cranium. And now if you don't know that head equals cranium, they're not going to be considered equivalent. And so we work to create these systems so that we can establish a way to get around that. Try to make the data presentation beautiful to reflect the effort that goes into every experiment. But the most important things that we think are essential is that you know who created the data and how you can get in touch with them. So all contributors are invited to use their ORCID identifiers so that anybody who wants to establish a collaboration can actually reach out and talk to that person. You can access this data and reuse this data using a CC BY license. And so attribution is your only requirement. You can see the interpretation of this data because we link the primary publication. So the data set has a DOI, the publication has a DOI, and those two things should cross-relate to each other. So you can find them whichever way they're published. Another thing that we think is pretty important is versioning. Just like you can, have different releases of software, you can have different releases of data. As you learn new things, as you perform new analyses, we want to make this a dynamic repository of information, not a static snapshot at a given time. And then it always includes information about the experiment in plain English. So we have a study purpose and curator's notes. The curators, take a step back because they didn't perform the experiment. And so as they help conform the data to FAIR standards, they also glean a little bit more information from the contributors themselves to say, okay, well, tell me a little bit more about that particular process. That's not something I'm not familiar with. How do let's put that into a way that non-domain experts can walk into that. So far we've got 55 terabytes of data. That's a lot of data. And so that's why this is such a big challenge. We really want to make sure that it's not 55 terabytes of data just sitting on a shelf that no one is going to access again. We want to make it reusable and usable for people who did not know that this was something they could have access to. There's over 350 data sets, and every data set comes with an experimental protocol that takes you step by step, just like a recipe. So it's not a methods section in a paper. It is truly the protocol so that you can understand exactly how that data was created. And in terms of access and making this data more equitable, we've been able to become partnered with the AWS Open Data Partnership. And so what that means is that all of this 55 terabytes in counting is available to everyone for storage and egress free of charge. So once it's published on the portal, it's free for you to use in perpetuity. So we really feel that that's a very important aspect of what our vision is for how data can really propel new discovery going forward. Just want to say that on the portal, all that effort to put in all of these of the metadata is actually used to make it more discoverable, more understandable, more findable. And so and it's findable. That's great, but if you don't know what you can do with it, that doesn't necessarily make you use it, right? And so we see the Spark portal not as a repository, but an ecosystem. And we have apps on the portal right now that represent ways that you can explore this data, but we also expect and hope to add to our apps list by community contributions. We're running a codeathon right now. I'll tell you a little bit more about that in just a hot second. But we want people to dive in, explore it, see what you got. You know, there's CT data, there's micro CT data, there's RNA-seq profiling, all sorts of stuff. But we also want to expand and integrate all this knowledge together to start showing where they're related and how they might be useful in terms of thinking about your experiment or your a problem that you want to address. And so it's great to know that there are data sets from the liver and there's data sets from the kidney or something like that. But how might data in the kidney be related to data in the liver? So we're building this peripheral nervous system connectivity map. And this is a knowledge graph that is built to relate all of the data based on how the body is innervated. And so it's a semantic knowledge base that is gleaned from the data itself, the experimental peer-reviewed publications, and direct contact with experts. And all of that is built into the knowledge base that powers the query, that powers the association of all these data sets together. And then layered on top of that is an AI agent for you to interact with that knowledge graph. So you can use it just like ChatGPT, but it won't hallucinate because it's only searching our database, not anybody else's. So it is quite a comparison to just ask these same questions of ChatGPT versus one that's constrained to our database. It's a lot of fun, actually. So just to give you a view of what this might look like. So in this case, these are our anatomical maps. As data is being contributed to the Spark portal, it gets integrated at multiple levels. So here's a visual demonstration of what this type of information turns out as. And so what this is a depiction of a circuit that innervates the kidney. And on the right side of the screen, you can see where those neurons start and where they terminate. So they terminate in the kidney, the glomerular capsule, all of that, and how they got there. And that how they got there, that routing, is really important for device creation. And also in thinking about a virtual experiment where you might say, okay, well, if I stimulate here, what else, what's impacted? What's downstream of that location? All of this data is peer reviewed or has provenance. And so you can just click to see how we got to that statement right there. We also show you how they're interconnected. So it's one thing to show a path like this that says, okay, well, it goes from the kidney to the spinal cord. That makes sense. But when you lay it all out, there's a lot of interconnection that happens. And so all of that's kind of important when you want to consider the signal integration that's actually happening. Those maps and models get a lot more complex and detailed as you dive in. And so we've got a whole body model that's 3D, as well as different species. So when you are looking to transition from, say, a large animal model, like Alex was talking about, those particular challenges of translating your animal experiments to first in human, this is a way that you can help inform that information. The data sets that exist already that are present, you can go right to them, and then from there you can actually do some in silico modeling if you would like. And I figured this might be where we might have some overlap. maybe. And that the challenges in computational modeling are the same challenges that are present in experimental wet lab applications too. Reproducibility and sustainability. Will it still work in 5 years? How do you know what input parameters and input data were used at the time that you ran that simulation? And what if you want someone else to use your pipeline, or someone else wants to collaborate with you? All of those things are not just a challenge of computational modeling. I mean, it's true in experimental wet lab work as well, but we're not going to be able to just ship our machine to people. And so OSPARC is free for you to use. If you do any modeling or you want to do any data analysis, please take advantage of this very powerful online cloud-based computational pipeline. Its primary purpose, these are a little bit old, is to give you the power of prediction. You can do multi-scale, multi-physics modeling for these electronic applications. You can also do it just to play around with your own particular analysis routines for different types of image data, for example. There are modular building blocks and explorable data analyses that are already integrated into the system. And so these things are there for you to use. It supports CAD design. So if you've got your device and you want to see how well your cuff will fit on a nerve of a particular diameter, and then model what happens if the nerve is a little bit smaller than your cuff, for example. Those are things you could do. But you don't have to be a computational modeler in order to do this. We've got guided workflows and a cookie cutter service creator. So you can just say, oh, I'm going to take this application and combine it with this one and this one. And it's meant to lower the barrier for this type of computational problem modeling. It does support verification and validation processes, as well as uncertainty quantification. So all of these things that really take a lot of time and can be very expensive if you have to do it experimentally. You can do it in silico, and it can provide a really great prototyping it'll be available on demand for everybody to watch. So all of those things are where we're at right now. We have this ecosystem that we've built over these years with the NIH funding, and we are working to build a community that spans many disciplines and experimental modalities, and all of these things sound great on paper, but the activation energy to go from that into a community that can see this as a place to go, an opportunity to use what's there and contribute their own ideas and own outcomes back to this, is where we're at right now. And so we do want to establish data sharing and data reuse as a consistent part of research dissemination. And we're trying to build the community. So we work to share the information, the outcomes of these research studies as broadly as we can. So we've got a LinkedIn presence, we've got a presence on Blue Sky, we've got a newsletter, and on the portal itself, we have a news section that basically provides sort of a breakdown of not just the outcomes of research, but sort of how you got to that place. So it's more of a, how did you get to the point of devising your experiment, going through the challenges of collecting and creating that data and interpreting it, and how can people take what you've provided and use it as a springboard to go to the next thing. This morning, it's always a lot of fun. We've got 7 international teams right now developing innovative projects that build off of our open source application. So the portal is open source. The resources that we've created are all open source. You can access the GitHub. You can contribute things that you think would be useful. And that's what these people are doing right now. So I'm really excited that this is going on, and we'll have an announcement next Monday with the winners of the project. The challenge with this is that we really want to entice people to start using other people's data, right? So people who do modeling are really comfortable with that because they're not actually running wet lab experiments to actually generate the data in the first place. But for the rest of us, we're typically in one camp or the other. And so building that bridge is something that we've been working on for the last few years. We also have a seminar series in hopes of trying to share just the breadth of information that people are doing and what types of challenges they're running into and what their successes are as they're building and presenting their research. And I'm looking forward to continuing to support that. And then lastly, we have, I mentioned that we've got an apps page where applications that can springboard off of data that is available on the Spark portal or represent an application that can be of use to this concept of bridging the body and the brain can be shared. So you've got a tool that relates to this, you can just list it on our site, and we'll help direct people to find new operations. And so basically our challenge is this: we need to transition from the focus provided by our funder, NIH, to become self-supporting. We really believe that it's really great to bring such diverse people together. Your computer engineers, your hardware folk, your experimentalists, and ontology. We want to bring these people together because we can do great things together, but they've already got their own place to go. And I think we want to become self-supporting, and we want to be community directed. And we want to leverage our strengths, those of us in the Data and Resource Center who are experts in our field, to help continue to build the community. And so with that, I just wanted to thank you for letting me introduce what we're doing here related to the Spark program. And I would love to talk to you if you have any thoughts about what you particularly like about your community, things that you this appeals to you, and what we might be able to do to give a bigger seat at the table on the Spark portal for hardware. So thank you.
For sure. Thanks. Great job. All right, and with that, we're going to take a 10-minute break and come back at 3:40 for our last round of afternoon talks. here on WAK 109. All right, everybody. So now as we get set and go back to our seats, we have our last set of afternoon talks. So our next speaker is Anthony DeFranco. He is the president of the Open Insulin Foundation, which is developing open source technology and knowledge bases for local scale production of insulin and other essential biologic medicines. He's researched numerical computation, purely declarative probabilistic relation programming languages in the PhD program at UC Davis, and did freelance research in the fields of programming language theory and theory of computation. Anthony holds a BS in physics and a BS in computer science and mathematics from Yale University, where he studied control theory, statistics, and information theory, and neural networks. And with that, I will give it over to Anthony.
Thank you very much. I didn't know you were going to read that out loud. I would have made it shorter. All right, yeah, and thank you for having me here. I am going to try to address in a very broad way a number of themes and complaints that have come up in many people's work and presentations, and it's a lot in a little bit of time. So I have bonus slides at the end and everything. So I encourage you to scan that QR code so that you can enjoy at your leisure afterwards. Oops, here. 5 more seconds. All right. Okay, so I am going to try to cover the very broad history of the kinds of institutions that shape the conventions and constraints of business and regulation and the other factors that influence our work, and look at some of the flaws in that, some of the consequences, and how open source addresses those concerns. And it's going to start by looking at Open Insulin's work, but I'm going to try to get to the bigger picture themes that are coming up and bring them out explicitly when often they're in the background. And then, in some of what is in the talk and some of the bonus slides are in the form of a bibliography with comments more than me actually telling you what the point is. So it's, an exercise for the audience. So we are in many different relationships with the kind of incumbent research to business pipeline. Some people are engaging with parts of this. Some people are trying to avoid all of it, like me. Some people are going in and out, weaving and bobbing and so forth. But, it kind of starts with academic research where there's a combination of personal sacrifices and expenses you bear to get your credentials, and then you go and you apply and compete for your grants, and to go through all this process of getting credentialed and becoming a PI and getting grants that could take decades, and it takes hundreds of thousands to millions of dollars to do it, and then to get the grant money, and you're spending your grant money, and that's kind of the order of magnitude of what goes on the balance sheet that eventually needs to be recouped. And then you go and you want to take some of your technology to market, so it's going to take the form of a startup business probably, so you're going to look to take on another order of magnitude larger investment, hire a lot of staff, and a lot of them are going to kind of serve overhead functions rather than doing the engineering on what you want to do. This is another years to decades time frame that's involved, in an order of magnitude higher amount of money, perhaps millions to tens of millions of dollars. And then you're going to go to market, seek regulatory approval. You're going to have to do some form of clinical trials, put together and submit thousands of pages of clinical documentation of documentation of various things, including clinical trials. Go back and forth over another period of years to decades, and this is going to take another order of magnitude more money, tens of millions to hundreds of millions of dollars. And all of this, it kind of requires the support and or the permission of many parties that don't really have a direct stake in the outcome. People, and the most obvious version of that is that all of this money has to be made back with a multiple attached to it. So that really, really restricts what is in the scope of what can happen in this kind of system. So this, that's just the general context. I'm going to look at a curious phenomenon in the world with diabetes and insulin. I tried to make a very rough order of magnitude estimate of the death toll due to lack of access to insulin. So it was just a very crude methodology that I used. I just kind of counted number of people out there and how many didn't have access, and the consequences of that for type 1 versus type 2. And I arrived at a figure of 12 million per year, so a million a month. And that is about the same as all of the deaths due to World War II while it was going on, the fighting, the famines and refugee situations and everything. So that was the deadliest conflict in history. So for one family of diseases, one drug, that's already, has this, the failure of the system has this impact. It's comparable, same order of magnitude of the deadliest conflict in history. And unlike that, there's very little attention to ending this. What's going on with the supply of insulin? The cost of manufacture is about $1 to $10 per vial. We estimate that we can do with our methods for about $7 per vial. Meanwhile, the list prices are $300 to $600 per vial. There are 3 manufacturers. They have increased their prices in lockstep together for about 20 years. What is stopping people from entering the market to meet the needs that are not being met here? Well, there's quite burdensome regulation and many signs of regulatory capture there. Potentially anti-competitive practices by manufacturers. Then they're often being sued for the possibility of such behavior, as you can see here. And we'll look at this in a little more detail later. There are complex networks of exclusive secret business arrangements in the supply chain with, rebates and many negotiated payments among a complex web of parties. And, I think, Eve, you pointed out that, we have a system where bribery is called lobbying. Like in this other part of the system, bribery is called rebates and negotiated payments. So zooming out a little more again, the fundamental economics of the situation are just wrong. Just in case there are any economists in the audience, I'll be careful with my terminology. So palace economy, it's this idea of a significant or dominant portion of the allocation of resources being done through a central government. And we have that very literally in the form of, Medicare being a huge part of most institutions' budgets. And also there are many other factors that lead to that sort of result obtaining indirectly. And the business itself, it's built around a lot of monopoly privileges, such as patents, but not only, and cartelized production with, a small set of approved producers, and it's very difficult to enter and, become one of those blessed parties from the outside. And this is rationalized in terms of false claims. The standard logic that some employ here is that subsidies are needed for innovation because innovation is expensive and R&D is expensive, and all that stuff we looked at before is very expensive, and so needs to be subsidized somehow. And monopolies are supposedly an expedient and economic form of subsidy. However, we know that when all is said and done, those monopoly rents do not mainly go into R&D. They go into primarily marketing, and executive compensation is a significant portion of it for a lot of companies, and things like stock buybacks and stuff. And R&D is pretty far down the list. The result of this is that we have these kind of fiefdoms that are made up of cartels, and they all have captive customers. And if their needs aren't being met, they're out of luck. And if you want to work in any of the areas that are left unaddressed by this, it is a great risk and expense in trying to engage with that. So in contrast to that, falsified story about the role of monopolies, I have found great value in the work of Jimmy Schmitz, who is at the Minneapolis Fed, and he has a career that has a lot of good research on what effects they really have. So he finds, like the conventional theory does, that they drive up prices, but in addition, they also destroy most of the industry's productivity. So it's no longer able to meet most of the demand that's out there. And so just in economic terms, this is a very large deadweight loss. And when we're talking about medicine and medical devices and healthcare, this is also lives lost and quality of life lost. Another thing that he finds is that they use political machinery to limit the output of competing products by blocking low-cost substitutes. So that may go a ways to explaining what we're seeing with the previous examples I mentioned. So that is another reason why the total output falls far short of the demand, and it drives the poor out of many markets. So here is a GoFundMe for a mother who is trying to raise money for 1 month of insulin for her child who's just graduated and lost coverage. And that bill really is about $2,400 a month. When I had a little lapse in my insurance coverage, I was handed a bill that was almost in the same amount. And fortunately, I was able to sort that out. But if you can't, you can't. And then it becomes very difficult. The perverse incentives go to the biggest questions that we face. It really is profoundly sabotaging the social good. The example that I think is one of the most dramatic here is, and it's one that I relate to personally because I have type 1 diabetes and I am working on a gene therapy for it, and I have a good concept on paper, and I'm trying to get this done, and it's proven very difficult to get what I think should be the obvious interest in this. But here we have in an article by Antonio Regalado in the MIT Tech Review, an analyst at Goldman Sachs asked a troubling question about gene therapy. Is curing patients a sustainable business model? There's a kind of commonplace observation that a patient cured is a customer lost, but here are people saying it out loud in forums that matter. This is a real thing. So as many of us might agree here in this room, I think open source is a very direct answer to these structural issues. So we share knowledge in the commons, and that means that anyone can draw on it for any legitimate purpose, as long as they respect the rules that keep that commons viable. And we have production options open to us where we can produce in low overhead distributed networks, and we've seen that with people addressing supplies in pandemic situations and other under-resourced scenarios. More or less, we involve the stakeholders directly in the work and its governance, and there's much more potential for that as well, and that's built into open insulin's plans as well. And as a result of these and other factors, we can innovate much faster and at much lower cost. So to provide a little more context for that idea, the theory of the commons that got Elinor Ostrom 2009 Economics Nobel Prize is very apt here. We can have a commons of technology, and this can still be something that is a basis for quite viable, lucrative businesses. And this is something that has been proven in the open source software world for many decades. The technology itself is not exploited for essentially monopoly value. Rather, the technology is available to be applied by anyone for anything, but the skills and the know-how to apply it can be sold as professional services. And this is the basis of some of the most successful and lucrative businesses out there. Red Hat in particular was the largest software company acquisition to date when it was acquired. It was around $40 billion, I believe. And this can be done while respecting and promoting the agency of everyone involved and market principles like competition and innovation instead of undermining them. So the fact that this has been happening in certain areas of technology, computer software, and more recently computer hardware, and other areas that are relevant to our work here, this directly led to a milestone in diabetes treatment, which was the development of artificial pancreas systems. So closed loop control of blood glucose that reduce or eliminate the need to constantly be manually checking and adjusting the dosing that's going on. So this started off as efforts by just individuals in small groups reverse engineering the communications protocols and working without any resources, really any support. And they beat out all of the manufacturers in making a viable system for doing this. And this was something that they had been talking about for decades. I think the earliest research on this is from the earlier mid 80s. So this happened and got fairly mature about 10 years ago now. And I think it proved not just the viability, but the superiority in many ways of doing things this way. So in Open Insulin, we are looking at developing open source microbes and equipment for protein production and purification, and also the looking to all of this knowledge about how the business models work and develop the complete picture of how this can work in insulin and hopefully other areas where analogous things apply. So in the case of insulin and biologic and other drugs more broadly, there are already many small manufacturers known as CMOs or contract manufacturing organizations. And so whenever there is a reason to manufacture something where it is not being made at the very largest scale for the very largest possible market, such as academic research and clinical trials, it's usually done with the services of one of these organizations. And it's done quite safely, and the product is very high quality. The people who are doing clinical trials don't want to be doing that with the substandard product. So all of the knowledge of how to do that is there. So we're looking at adapting that and just using the same technical basis for production and using some of these business models that are open to us to include direct stakeholder ownership and management of the organization. And as the open source equipment matures, we can also cut the capital costs and build that into the commons as well. So this circumvents potentially the issues that we see with the very complex supply chain that that I mentioned earlier. They are not going to be open to that discussion. I mean, often it's even hard to initiate that, I found. So one example of what happens as a result of this is that, and there are things all through this network that are like this, but for example, a particular insurance company might only cover a particular brand of insulin because they negotiated exclusivity with that manufacturer through a pharmacy benefits manager. And a person who has a job that only offers that insurance, but for some reason cannot use that brand of insulin because perhaps the formulation they differ a little bit across brands, and that formulation may not agree with one, may make it ineffective or might be allergic to it or something. If that happens to you with your insulin, you get stuck with, going off the formulary and maybe only getting 50% coverage instead of just your standard copay. And so then that goes and it's referenced to these list prices, which are $300, $600 a vial now. So then you might end up with a bill of $1,000 or $2 a month, whereas, normally you would only be paying $35 a month or something. So, and there are all kinds of pitfalls like this as a result. So what we're looking at is replacing that supply chain with one that is much simpler and works this way. So we're doing our research in community biolabs, and we're producing open protocols for production. And we actually have a partnership with a nonprofit CMO in the DC area, and we're going to co-develop those protocols and document them and open source them. And then the ongoing work can occur in some combination of cooperatives that have the participation of the users of the insulin themselves and the smaller scale local CMOs and local pharmacies and hospitals that will be able to handle and oversee the dispensing of the drug. And we can make partnerships with local and state governments to legitimize this and codify how it should work and provide the oversight that needs to come from outside. And we have, in addition to just what's established in CMOs, there's a lot of interest in doing things at an even smaller scale that might further expand the scope of what we can do. And it's coming out of the personalized medicine worlds and the military and disaster preparedness worlds. And in order to organize these fundamentally cooperative organizations that are going to formalize how the users of the insulin participate in the governance, we're also looking at many precedents that may be more or less relevant. So cannabis cooperatives are quite striking in what they've been able to accomplish. They were, state level frameworks that mandated a cooperative structure and were able to permit an activity to be carried out that was perhaps the only thing that is more strictly regulated than what the FDA does. It's, under the DEA, and it's just a Schedule I drug, absolutely off limits. And in the end, it didn't really matter. And so we're also looking at, other historical phenomena of interest like buyers clubs, health insurance co-ops, lodge practice of medicine, and one that's dear to my heart, Discount Drug Mart is an employee-owned cooperative pharmacy chain in Ohio, where I'm from. And I think we have a lot of precedent to draw on here. So I'll quickly show some of the open hardware that we're working on in the project. This is, well, okay, so that in the blank video is a fraction collector that's using the positioning capabilities of a 3D printer, and you have a UV detector for the protein production system, and we're just working on a lot of plumbing, it's pumps and valves and such, and that's kind of how you run it's a macrofluidic system more to produce and purify protein. So this isn't as far along as the microbe research, but it is in the pipe. Another thing we're working on is a bioreactor design that's using common off-the-shelf parts, and this is something that could cost from maybe like $30,000 to $50,000 used in some cases to hundreds of thousands of dollars new. And we have a modular system here where you could add capacity in like 1 or 5 gallon increments, and each unit of that might come to maybe $150, $200 in terms of materials. Some of the parts were left off because we already had them laying around. So putting all this together, the costs can be reduced by orders of magnitude here. And this is entirely in keeping with what the FDA itself knows and advocates. They found that when you get to, and this is not even looking at the improvements we're making in terms of capital costs and such. This is just having more manufacturers. And when you get to 9 manufacturers, your eyes do not deceive you. That line is 0. So that is a negligible cost. And again, this is something that is part of official policy to advocate this, but things aren't coming together yet without a little help. Okay, so very quickly, I'm going to look at some of the history. So why are there all these contradictions and baffling failures here? So I am going to try to present some things that are suggestive that this corporate state finance business nexus that we're accustomed to was established in the form that it exists for the purpose of wealth extraction in an era of colonialism, and we don't like them for those reasons, and also they're not going to last for those reasons because there's nothing left to colonize and exploit. There's nowhere in the world left to conquer. The populations in the home countries are poor and immiserated, and that's it. So it's open source now, and so that's, I don't have time to fully defend that. So I'm just offering some readings to motivate and inform more rigorous engagement with these issues. Gabriel Kolko, we're going to go backwards in time. So he tells a story of how in the wake of the Civil War and the conquest of the West of America, this created large industrial, financial, and commercial interests that were symbiotic with the government, which is a fairly new thing in America. And then they consolidated into a formal economic regime in the following decades. And regulations are one of the regulatory regime and philosophy that we have is one of the products of that. And so the way that was done, the specific way that it was done, had a lot to do with preempting state and local regulations and doing it in a way that catalyzed the formation of cartels. A lot of homework there for you. And a reaction to that sort of thing, Black Panther's survival programs. So they had a whole range of mutual aid services that were filling in the gaps that were left by, very broadly speaking, this kind of development. So medical clinics, sickle cell anemia research foundation, free dental, free optometry, free ambulances, free food, free breakfast, food co-ops, news service, community employment, shoes, clothing, legal aid and educational program, busing to prisons, etc. Let's go back in time a little bit. So let's go to the dawn of the early modern era. Vernacular Values by Ivan Illich. He was a renegade clergyman and ran a school in Mexico, and he made good use of the Vatican archives, dug up all of how the Castilian Spain and the church collaborated to engineer social institutions to create dependence. And they used this within Spain, they used this to colonize the Americas and extract wealth from them. And on the heels of this, the corporate forms were created to finance expeditions to do this sort of thing. And we got the companies. No coincidence that both a paramilitary expedition and a business organization are called companies and have officers and so on. And they went and did what they were going to do. A lot of this came home in the phenomenon known as the imperial boomerang. It drove people to leave Europe and to go to North America, which we just talked about. Part of what happened in this context was the Salt March. So this was part of a broader philosophy of economic self-sufficiency. The British had a salt monopoly, very heavily taxed. People realized you could just go and get salt water out of the ocean, dry it in the sun, you're done. Everyone who did so was savagely beaten, and nonetheless, that was even worse in the end for the future of the British Empire in India. Go all the way back to the Roman Empire. David Graeber in his book, Debt, the First 5,000 Years, covers a lot of this. Also, I saw this truck parked outside during lunch. Delivery truck, Roman Empire Logistics LLC, so still with us. So the Roman army, they would go out and they would conquer, inaugurate a new province. They wouldn't just kind of conquer it and leave. They would stay around and they would impose a military regime and they would impose taxes and that had to be paid. And that would let the soldiers that were staying around and occupying be supported by the people there. And it would remake the whole society in such a way that they could extract wealth and deliver it back to Rome. David Graeber also observes in this example and others that the best definition of slavery at the individual level and subjugation at the societal level that he can come up with is the condition of being cut off from social relationships from which one derives mutual aid. So, concluding thoughts in the form of quotes. William Blake, a prophet of sorts from the imperial era of Britain. War is energy enslaved. We've seen a lot of this in various forms, and this is one that cuts in many different directions here in what I'm talking about. Alan Kay, beloved figure in computer science. A change in perspective is worth 80 IQ points. Tim O'Reilly, a beloved figure in open source. Create more value than you capture. Okay, and then these are the extra credit slides that are all very interesting that you can read on your own when you download the slides, which you can do with this QR code here. And thank you very much. Thank you for your time.
All right, then. That was phenomenal. So now I have one more talk, and then I want to say thank you so much for allowing me to MC you guys today. And when you go next, you will hear the wonderful voice of my colleague, Heron. But next, we have two presenters, Randall Manning, who is an occupational therapy student and a researcher working with UTMB's medical prototyping lab. He is interested in sensory substitution, product design, and its applications for therapy. We also have Vivek Ananda, who is a medical student and researcher working in UTMB's medical prototyping lab, and his interests are neurological rehabilitation, PM&R, and pediatrics. The talk that they are going to have is called AMP Touch, Adaptable Listening Prosthetics for Sensory Loss. Okay.
Good afternoon. My name is Vivek Ananda. I am a third-year medical student at the University of Texas Medical Branch down in Galveston, Texas. And I am very interested in the field of physical medicine and rehabilitation. It's a newer field in medicine, but within it, I am very interested in spinal cord injury, traumatic brain injury, as well as the interventions that can be done to manage it.
Yep, and I'm Randall Manning. I have a bachelor's in kinesiology and exercise science with a focus in biomechanics, and then I'm finishing up my doctorate in occupational therapy with a focus in assistive technology. And we're working at the UTMB prototyping lab under Dr. Chassin.
And as we begin today, I'd like to pose you guys a question to think about. Is it possible for us to feel without our fingers? And as we think about this, I'd like to tell you guys a little story. This story is about John Powers, an artist. On May 19th, John Powers was cutting wood on a table saw when the table saw kicked back. It dragged his hand through the blade and severed his thumb and ring finger and injured his middle and index. Luckily, his pinky was spared. When wheeled into surgery, he talked to the people there, and he said a really poignant statement that I think tells us a lot about the importance of his work. And he said that, "I think with my hands." We have a couple images here of his work, and it shows us it's a very physical, very real kind of art that requires your hands.
So a little bit more about the open paw. So this is the open call that John created during his rehab process. So this was a call to engineers, designers, and artists. He wanted to create a movable feast with his hands. But what really spoke to me as an occupational therapist and as a clinician was this last part. But first, I need to be able to pick things up and hold them, because we can create all these fantastic, like delicious things, but if you're not able to function, kind of what's the point?
So as our lab began to think about John's open paw, we came up with some issues with the current status quo regarding prosthetics. And one big thing is that current prosthetic technology lacks meaningful sensory substitution and often requires visual input to use a prosthetic. This limits the functionality of the prosthetic, increases mental load, and also contributes to device abandonment. In addition, the sensory substitution that is there is often directed toward functional grip force attenuation and movement restoration. So if you're picking up a cup, making sure you don't crack it, rather than feeling how the cup feels. In addition, amputation has a lot of wide-ranging impacts. One big thing that I'm very interested in is the neurological impacts that it has, as well as things like phantom sensation, telescoping, and phantom pain that can really affect one's function as well as quality of life. And next, the available medical interventions that we have, like targeted sensory innervation and nerve grafting, are invasive, expensive, and importantly, don't offer any guarantee of success. And finally, prosthetics are still incredibly expensive and difficult to obtain. Even though we have really cool things like we heard about yesterday with the open source leg, affordable, timely, and innovative solutions still are needed. So this is our product, it's called the AMP Touch, and it's a proof of concept that is a simple, low cost, and most importantly, a non-invasive alternative that delivers tactile information via auditory feedback. So it leverages a set of off-the-shelf components, being a contact microphone, a Bluetooth transmitter, a receiver, and a headphone to deliver what you're touching feels like to your ears. And 2 prototypes have been made. One is a custom variant for John that replaces the distal phalanx of his right thumb, as well as one that can wrap around healthy and prosthetic fingers to make sure that this technology is accessible to all.
So we started this off, this was based on the research of Paul Baccarita and Gordon Lundberg, but we kind of started this process with what we had in the lab. So what you're looking at is we just had an Arduino, some microprocessors, a microphone, and a speaker. This piece was really just kind of more of like a proof of concept just to make sure the whole thing worked, and it kind of did. We were able to hear stuff with it, but we had power regulation issues and volume output issues. We fried a couple Arduinos and microprocessors, so we kind of moved over to more of a traditional prototyping. Moved over to more traditional prototyping. We used a breadboard, and this is where we really kind of tested the different types of microphones. So we were trying to decide between condensers or piezo microphones, and this is where we decided to focus on the condensers, just because it's a little more, it's stronger, it has better sound fidelity and provides more nuanced sounds. But we did decide to keep the piezos for a different model, just because of the smaller profile, and it is particularly sensitive. So at the end of that one, we decided we were still having regulation and power volume issues with that one, so we moved over to more of like a traditional hack. So this is a Bluetooth, no, it's a wireless microphone that we kind of hacked. So we opened it up. I put in a stronger and longer wire, and we embedded the microphone into the fingertip. And then we also added some elastic hand straps to hold it in place on the wrist. And then we removed the male end of the earpiece and put on a female end so it can just plug directly right into the transmitter or the receiver. So this is version 2.2. This is the second one. So we added the dual finger cuffs for a couple reasons. One, it provides a little more natural sensation experience, because usually whenever you kind of rub textures together, you're doing it between your fingers. And then also it's you can just slip it right on over your fingers or other prosthetics, so it's quite easy installation. So this is what we sent to John. So we sent him we sent him both of the products. Then we also sent them 2 testing kits, which I'll go over a little bit more in a second. So the first one, this is a stereognosis kit. So if you guys don't know what stereognosis is, this is kind of your ability to see with your hands. So what this, how it looks is, say if you're searching through your backpack or your purse, and you're trying to find your keys without looking, you're trying to searching through and you're like, okay, that's my chapstick, that's my phone, that's my wallet, that's some mints. Then you finally find your keys or your phone. Like that's stereognosis. So whenever we do this in like traditional medical settings, we you kind of pre-discuss the products or the items that are in the kit, so the person knows what they're could be looking for, but the vision is obscured. But we did it a little different this time. So we did it with he was not aware of what the items were in the kit, and he also did it with vision obscured. We decided to do it this way because we really wanted to kind of test the device and see how like how capable it was. But he was able to do it. He got all of them. Took him about 15 minutes to do it the first time. Then we did 3 other rounds. So the second one, we did it with a non-involved hand. That took him about 4 minutes. And then we did it again with the device, with the involved hand, with the device off. That took him about 3 minutes. And then we did it one more time with the device on, and that took him about 4 minutes. He did mention that the foam disc was kind of difficult to identify, and the shell was also a little difficult, but that's kind of like an odd object. Most people don't run into that, but you know, we're from Galveston, so I kind of had to slip a little something of us in there. And then also there's that string. So that's a pesky little string. So it's just kind of hard to find that down at the bottom of the packages and stuff, and just kind of pick it up was just kind of difficult. And so for the fabric discrimination test, so yeah, he was able to get most of these. So kind of starting from the top left, you have a synthetic silk, then you have cotton swatch, then you have a ripstop nylon, then there's a piece of wood, denim, paper towel, synthetic fur, and then the bubble wrap. So he was able to, like, again, most of these, he did comment that the denim was particularly like unique and had a unique sound signature. So that one was like kind of nice to interact with. And the same thing with the bubble wrap. I mean, bubble wrap's fun. So everybody can enjoy playing with some bubble wrap. And he did mention that the cotton was difficult to identify just because it's particularly thin and just kind of hard to manipulate, and it didn't have a super strong sound signature. And then the wood, I think he initially identified it as plastic, but it's particularly smooth. And I also think it might have been a composite material, so it's not just wood.
So our findings when talking with John were really positive, and we were excited to hear that the device did have function and it did allow John to discriminate objects. So first, talking about stereognosis, John was able to correctly identify 13 out of the 13 objects in the pouch after some time, which does show that the AMP Touch does provide the user an ability to have stereognosis. There is a caveat that John did state that his pinky does retain some sensation, so that it's not a perfect experiment, but what we aim to take away from that specific test is that it does have that discriminatory ability. And when going into fabric discrimination, John went into this blind. He couldn't see anything and was able to identify 6 out of the 8 fabrics using the AMP Touch, which we thought was really positive. This shows that not only is the AMP Touch able to tell you about just the shape of things, but also when you just feel it, what is it? Which is a really important characteristic of what we wanted to achieve with the device. Some other findings that we had along the way was that replacing the appendage didn't require too many tools, and swapping between them was feasible. So this item does allow us to know that the AMP Touch could be used in specific situations and doesn't have to be a daily use kind of device. Finally, two other really interesting things that we found was that density was able to be determined by generating impulse sounds or tapping. So by tapping the device on an object, you could approximate what its density was. And in addition, by doing something called scanning, so by moving one's finger along the side of an object, you could approximate its shape and contour by when the sound changes and when it stops. So two really functional pieces of information that you can use the AmpTouch for. However, there were some, yes, sir?
The impulse sounds and said, oh, this is less, this is that. I mean, how does he, where's the signal from the impulse sound into his finger, and how is that reaching his brain? Say, oh, okay, this sound sounds like this, feels like this. This sounds
Yeah, so
like that.
it's a headset.
Right, and
It's a headset. It goes into his ears. So so this is kind of based off of neuroplasticity. So he's interpreting the sound with sensory substitution. So he hears the texture. So like versus, yeah.
But yeah, so it did have function. And we'll get more into our future plans with it to kind of get to it. But there were some improvements that we had to make. One thing is that for this AmpTouch to give you any sort of information about what you're touching, it has to be in contact with the mic. So if an object is in contact with the mic and there is an amount of movement, it'll generate a sound that's unique to what you're touching. So when it does do that, you have to grip it pretty well. And the material that we cast the original device for John out of was relatively hard, and he wasn't able to grip objects with it that well and hold them there. So we are intending for our next variants to cast it out of silicone resin or another tacky sort of material so that items can be gripped well and they can be heard. In addition, we need to relocate the mic on the AmpTouch itself so that we're thinking something more distally and medially toward the side of the thumb so that it comes into grip when you naturally grip things. It comes into your finger. And finally, we'd like to add more microphones to the AmpTouch to create a sort of sensor array so that you can get a variety of sounds that inform you more about larger objects and things like that. So with respect to our plans with the device, we are currently preparing for an IRB submission for a study that has an increased sample size of both prosthetic users as well as able-bodied users to determine the real functionality of the device. And we plan on using a variety of psychophysical testing methodologies to determine the AmpTouch's ability to, A, distinguish between different textures. So you guys, so we talked about the fabric swatches. This is kind of that concept. So our first idea was something like sandpaper grits. Can we use the AmpTouch, simply feel it, and from the information it gives you, tell you, okay, this is maybe closer, this is rougher, this is smoother, this is 110 grit, this is 150. In addition, we want to find out how well it's able to distinguish objects without visual feedback, the stereognosis testing, but just done in a more controlled environment. As well as now with the ability, we'd like to determine its ability to estimate density of objects. So overall, we'd like to quantify the functionality of the AmpTouch, but also further research in sensory substitution as a whole for tactile and auditory stimuli to see if this is a viable method to deliver information. So the overall umbrella of this is something called modality mismatch sensory substitution. So taking one sense and substituting it for another. And that concept is relatively underrepresented in prosthetic sensory research. And we hope that more research in this area could lead to innovative solutions that leverage this concept. It doesn't have to necessarily be touch and audio. It could be any of our 5 senses or even more. And swapping those could lead to interesting and innovative solutions.
So some of the healthcare implications for this is that you know, we could possibly reduce the risk of phantom sensation. So whenever someone undergoes a traumatic amputation, the brain begins to very quickly rewire itself. So it undergoes cortical remapping, and then during this cortical remapping and rewiring is when they think a lot of like the risk for phantom sensation occurs. But there's also research that suggests that if you can provide some level of associative input into that area, it reduces that risk. So like you're kind of the neighbors of that part of the brain that processes like the finger or the hand, they take that over very quickly. So being able to provide it something can reduce the risk of phantom sensation. And then also, this potentially can increase the adoption rate of prosthetic devices by reducing the cognitive load whenever during the initial training phase. It can reduce the frustration, and then also just kind of giving it more of a meaningful piece to interact with can help during the initial training phase. And then also there's improved occupational performance and task efficiency. So occupational performance, I'll kind of go on that real quick as an occupational therapist. Kind of what that means is it's like how you occupy your time. So that could be like your job, your work, your hobbies, folding your laundry, activities of daily living, things like that. So pretty much anything that you do in the scope of OT is like an occupation. So you can just see functional improvements. That's a possible benefit. And then also, this is it's a new tool. It's an inclusive client-centered tool that we have available as potentially have available as clinicians to offer to our clients and patients.
So with our project's implication for open healthware, one thing that we focused on for this project is that we want it to be low complexity as well as high replicability, something that people can make for themselves and use. And when we did this, we wanted to ensure about its cost. The current cost we estimate to be about $50 for someone to make this themselves, made mostly of off-the-shelf parts, which are accessible and available. And an important one for Randy and I was that it requires minimal technical skills to construct. Randy and I are not engineers by any sort of state of the word. I spent my last 2 weeks delivering babies, and Randy, and this was our first time ever soldering, stuff like that. So the fact that our focus in trying to make it easy for us to make, I think also lends itself well to open healthware, that anyone should be able to pick this up and make it for themselves if it could be useful to them. And from the perspective of future clinicians, we hope that open source technology will increase its accessibility to users and clinicians. So a little bit of background about us is that in Galveston, we're about a 1-hour drive from the Texas Medical Center in Houston, which is probably one of the biggest medical centers in the world with some of the most cutting edge, bleeding edge research being done. But Galveston is a very different place where it's a relatively resource poor area that's very diverse. And having tools in our pockets, both Randy and I work at clinics, like a free clinic called St. Vincent's, and having tools like these could be really impactful for when people come to areas like this where clinicians are able to give alternatives. So some takeaways for us are that audio tactile sensory substitution is feasible. And from our results with John, this shows that this is an area of research that should be continued. And in addition, open healthware can improve access to care for patients. And a good thing for us is that limited engineering skills is not prohibited to get started. It doesn't require a degree, and it's possible to create something that does give function to someone without any sort of prior experience. And our goal for this project is an open source integrated solution. While we did use off-the-shelf parts right now for this variant of it, we hope to create an integrated electronic solution in the future, maybe when we develop a bit more engineering ability.
Just real quick on a kind of a personal note, it's been really like empowering and inspiring and kind of humbling to be a part of this. Like as Vivek mentioned, like a year ago, like I could hardly even solder, and now I'm able to, like I'm standing up here talking to you guys, and like we created this cool device. So just this open healthware like process, something that's going on here, like I'm just really thankful to be involved with it. And then also seeing stuff like the open source leg, like I could very easily see this type of product, our product, moving into that to contribute to research. So that's something I just never even thought of when I first started out with this.
Research and community. I really liked how open source leg talked about community. And finally, if projects like I know Alex and OpenNerve are able to do class 3 really strenuous things, I hope that projects like ours, a class 1, are able to make open source healthcare a reality. Thank you for listening to us. This is Francis Bacon, John's dog, getting some stereognosis testing.
Hi, all. We're going to be closing out the day. So I really just want to say thank you for attending. Thank you to NSF for funding and making this happen. If anyone told me 5 years ago that I would be sitting in a room with people making devices open source to get people to hold things, hear things, see things, touch things for the first time in years, I would not have believed them. It's been a very cool journey with OSHWA. I've been so happy to be a part of this community coming from reproductive healthcare, and we all know how that's going in the state of the world right now. So I'm really thankful for all of you. I want to just say that we are going to be sharing social media, so please plug in. My job as the community coordinator is literally to connect you all with resources, people, organizations that can help you. So I have business cards. Please take them. Please bother me. I love connecting people. I love seeing where people fit. So please don't hesitate. We cannot do this without each other, and I think everyone has learned that and everyone has voiced that when talking about it. So please come up to me. Please socialize. We look forward to building this ecosystem further, and this is a very beginning of our journey at OSHWA. This is our first ever Open Healthware conference, and we're hoping to continue. Part of that is going to be in the service. Thank you. So if you can take the survey and do it and share it with other people who are in these fields, that would help us so much, because we are literally building this from not scratch, but from a beginning for OSHWA. So please fill out the survey. We really want your feedback. That's why we're talking about it and bullying you into doing it so bad. And the OSHWA team will be hanging around. So please say hi. We'll be here. So connect with us, as I said. And yeah, take some food home, please. Have a good rest of your day, and I hope you guys enjoy New York and you enjoyed the conference.